Hello there, and welcome. Tonight I want to take you somewhere far beyond the familiar boundaries of our everyday world, somewhere into the vast, quiet expanse that surrounds our small blue planet. It's a journey not of distance, but of perspective, and perhaps, just perhaps, it will change the way you see the night sky forever. As you settle in, letting the weight of the day slowly dissolve into the softness around you, I want you to consider something that might seem impossible at first, something that scientists have only recently begun to whisper about in the hushed corridors of observatories and research centres around the world. You see, we live our lives believing that the grand architecture of our solar system is fixed, permanent, as unchangeable as the mountains or the oceans. The planets spin in their ancient paths, following routes they've traced for billions of years, and we assume they'll continue this way forever. It's a comforting thought, isn't it? This cosmic stability, this celestial clockwork that ticks away above us each night. But what if I told you that recently something visited us from the depths of interstellar space, something that might have left a mark so subtle, so gentle, that we're only now beginning to understand its implications? What if the passage of a single object, a wanderer from another star system entirely, could actually shift the very orbits of the planets themselves? Now, I know what you might be thinking. This sounds like science fiction, like something from a movie or a novel, and yet, the object I'm talking about is very real. Its name is 3I Atlas, though you might know it better as Comet Atlas, discovered not so long ago as it swept through our solar system on a path that originated somewhere impossibly far away, in the darkness between the stars. The I in its designation stands for interstellar, marking it as only the third confirmed object we've ever detected that came from outside our solar system. Think about that for a moment. In all of human history, with all our telescopes and satellites and space missions, we've only confirmed 3 visitors from the vast ocean of interstellar space. And this one, this mysterious traveller, might have done something we never expected. As we begin this journey together tonight, I want you to let go of any anxiety or fear about what this might mean. This isn't a story of catastrophe or collision. No, this is something far more subtle, far more beautiful in its implications. It's a story about the delicate dance of gravity, about how even the smallest partner in a cosmic ballet can influence the steps of giants. It's about timescales so vast that entire civilizations could rise and fall in what amounts to a single heartbeat of the universe. And perhaps most wonderfully, it's about how we, tiny beings on a small planet orbiting an ordinary star, have developed the ability to detect and understand these almost imperceptible cosmic whispers. If you're finding this intriguing yet soothing, perhaps you'd enjoy exploring more cosmic mysteries with us. Consider subscribing to our channel, where each night we unravel another thread in the vast tapestry of the universe, always with the same gentle curiosity, the same peaceful wonder. But for now, let's continue our journey into this particular mystery, this question of whether a visitor from the stars might have gently, almost tenderly, altered the very structure of our cosmic neighbourhood. The story begins, as many astronomical discoveries do, with a faint smudge of light noticed by automated telescopes scanning the heavens. It was December 2019 when the Asteroid Terrestrial Impact Last Alert System, or ATLAS, first detected what appeared to be a new comet. At first, there was nothing particularly unusual about it. Comets are discovered regularly, these dirty snowballs left over from the formation of our solar system, usually orbiting far out in the cold depths beyond Neptune. But as astronomers track this new object, calculating its path backward and forward through time, something extraordinary emerged from the mathematics. This wasn't one of our comets. The trajectory was all wrong. Instead of the closed ellipse that would keep it bound to our sun's gravity, this object was on a hyperbolic path, a trajectory that meant it had come from somewhere else entirely, from the vast emptiness between the stars. Imagine that for a moment. While you've been living your life, going about your daily routines, this ancient traveller has been sailing through the darkness for perhaps millions of years, moving through the empty void at speeds we can barely comprehend until finally, by pure cosmic chance, its path intersected with our solar system. The implications are staggering when you really think about it. Space is so vast, so empty, that the odds of such an encounter are almost infinitesimally small. If you were to shrink our entire solar system down to the size of a quarter, the nearest star system would be about 500 feet away, and between them, nothing but emptiness. For this comet to have travelled from another star and passed through our solar system is like throwing a grain of sand from New York and having it pass through a particular window in Los Angeles. The universe had to align in just the right way for this meeting to occur. As 3I Atlas approached the inner solar system, astronomers around the world turned their instruments toward it, eager to learn everything they could about this rare visitor. What they found was both familiar and alien. Like our own comets, it was made of ice and dust, materials that are common throughout the universe. But the specific mixture, the ratios of different compounds, told a story of formation in an environment very different from our own solar system. This object had been born around another star, under different conditions, perhaps billions of years ago. The comet brightened as it approached the sun, just as our local comets do. The sun's heat caused its ices to sublimate, turning directly from solid to gas, creating the characteristic fuzzy coma and tail that we associate with comets. But even this familiar behaviour had subtle differences. The rate at which it brightened, the way it responded to solar heating, all provided clues about its alien origin. Scientists watched in fascination as this messenger from another star system performed its brief dance in our sky. And then, something unexpected happened. As the comet continued its approach toward the sun, it began to fragment. This isn't entirely unusual for comets. Many break apart under the stress of solar heating and their own rotation. But for 3I Atlas, this fragmentation meant that instead of a single gravitational influence passing through our solar system, we had multiple pieces, each following slightly different paths, each exerting its own tiny gravitational pull on everything around it. Now, when we talk about gravitational influence, it's important to understand just how subtle these forces can be. The gravity from a comet, even a large one, is infinitesimally small compared to the massive pull of the sun or even the planets. It's like comparing the gentle breath of a sleeping child to a hurricane. And yet in the precise clockwork of orbital mechanics, even the tiniest force, applied at just the right moment, can have consequences that ripple outward through time. Think about it this way. Imagine you're gently pushing a child on a swing. Each push is small, barely noticeable, but if you time them just right, matching the natural rhythm of the swing, those tiny pushes add up. Over time, the swing goes higher and higher. In the same way, a small gravitational perturbation, perfectly timed, can gradually alter an orbit. The change might be imperceptible at first, measured in meters or even centimeters over the course of years, but given enough time, those tiny changes accumulate. This is where our story becomes truly fascinating. Because 3I Atlas didn't just pass by Earth or Mars. Its trajectory took it through the heart of our solar system, passing relatively close to several planets. And as it did, it engaged in a complex gravitational dance with each of them. The planets pulled on the comet, altering its path, speeding it up or slowing it down slightly. But Newton's third law tells us that for every action, there's an equal and opposite reaction. If the planets pulled on the comet, then the comet must have pulled back on the planets. The question that keeps astronomers awake at night, the question that we're exploring together in the quiet darkness, is whether those tiny pulls might have been enough to measurably alter the orbits of our planets. It seems almost impossible, doesn't it? These massive worlds, some of them hundreds of times more massive than Earth, being influenced by a relatively tiny comet. And yet, the mathematics doesn't lie. Every object with mass exerts gravity, and every gravitational interaction, no matter how small, has an effect. To understand this better, we need to think about the concept of orbital resonance. You see, the planets in our solar system aren't just randomly placed. Over billions of years, they've settled into a complex pattern of orbital relationships. Some planets complete exactly 2 orbits in the time it takes another to complete 3. These resonances create a kind of cosmic harmony, a stable configuration that has persisted for eons. But this stability exists in a delicate balance. A small change to one planet's orbit can affect the resonances, which in turn affects other planets, creating a cascade of subtle adjustments throughout the entire system. Scientists have been running complex computer simulations, trying to model exactly what happened when 3I Atlas passed through. These simulations take into account not just the comet's mass and trajectory, but also its fragmentation, the solar wind, the gravitational influences of all the planets, and countless other factors. Each simulation runs for simulated millions of years, tracking how tiny changes might propagate through time. And while the results are still being analysed, still being debated in quiet conference rooms and through lengthy academic papers, some intriguing possibilities have emerged. One simulation suggests that the passage of 3I Atlas might have altered Earth's orbit by a few hundred meters. Now, that might not sound like much when you consider that Earth orbits the Sun at an average distance of about 150 million kilometers. A change of a few hundred meters is like moving a single grain of sand on a beach that stretches for miles. But remember, we're talking about cosmic timescales here. A change of a few hundred meters now could mean a change of thousands of kilometers in a million years, and perhaps millions of kilometers in a billion years. Another fascinating aspect of this cosmic encounter is the timing. 3I Atlas arrived at a particular moment in our solar system's history, when the planets were arranged in a specific configuration. If it had arrived a few years earlier or later, the gravitational interactions would have been completely different. It's as if the universe rolled cosmic dice, and they came up with a particular number that we're only now beginning to decipher. This randomness, this element of chance in the grand machinery of the cosmos, adds a layer of wonder to our contemplation. Consider also that 3I Atlas is just one of countless interstellar objects that must pass through our solar system over geological timescales. Most of them are too small or too distant for us to detect with our current technology. They slip through like ghosts in the night, their passage unmarked and unnoticed. But each one, no matter how small, adds its tiny gravitational signature to the complex dance of our solar system. Over millions and billions of years, these countless small influences add up, slowly reshaping the orbits of the planets in ways we're only beginning to understand. This brings us to a profound realization about the nature of our cosmic neighborhood. We tend to think of the solar system as isolated, protected, separate from the rest of the galaxy. But 3I Atlas reminds us that we're part of a large community. We're not alone in our journey around the galactic center. We're constantly passing through regions of space that contain debris from other star systems, and occasionally, as with 3I Atlas, we have close encounters with objects that formed around distant suns. In a very real sense, these interstellar visitors are messengers from other parts of the galaxy. They carry with them information about their places of origin, frozen into their chemical composition and physical structure. When we study them, we're not just learning about a single comet or asteroid. We're learning about the conditions around other stars, about how planetary systems form and evolve, about the incredible diversity of worlds that must exist out there in the darkness. The story of 3I Atlas also highlights the remarkable capabilities of modern astronomy. Think about what we have accomplished here. We've detected an object perhaps a few kilometers across, traveling at tremendous speed, coming from interstellar space. We've tracked its motion with such precision that we can calculate its trajectory backward for millions of years and forward for millions more. We've analyzed its composition using spectroscopy, essentially determining what it's made of by studying the light it reflects and emits. And now, We're calculating its gravitational influence on bodies millions of times more massive than itself. This level of precision would have seemed like magic to astronomers of previous generations. Johannes Kepler, who first worked out the laws of planetary motion, could never have imagined that we would one day be able to detect such subtle influences. Isaac Newton, who gave us the law of universal gravitation, would be amazed at our ability to apply his equations to such complex multi-body problems. We stand on the shoulders of giants, using tools and techniques that push the very boundaries of what's possible. As you lie there in the darkness, perhaps you can feel the earth beneath you, this massive sphere of rock and metal and water, spinning through space at tremendous speed. Right now, as you listen to these words, we're orbiting the Sun at about 30 kilometers per second. That's fast enough to circle the Earth's equator in about 22 minutes, and yet this motion feels perfectly stable, perfectly predictable. The idea that a visiting comet could alter this seems almost absurd, but this is where the wonder really lies, because the universe operates on scales of time and space that dwarf our human experience. What seems fixed and eternal to us is actually dynamic and changing on cosmic timescales. The continents drift across the face of the Earth. Mountains rise and fall. The moon slowly spirals away from us. And yes, the orbits of the planets themselves gradually shift and change, influenced by countless factors, including the occasional interstellar visitor. This perspective can be both humbling and oddly comforting. We're part of a universe that's constantly in motion, constantly changing, constantly evolving. Nothing is truly permanent, not even the paths of the planets. And yet, this change happens so slowly, so gently, that life has been able to flourish on Earth for billions of years. The changes we're talking about, these orbital shifts potentially caused by 3I Atlas, would unfold over timescales so vast that thousands of human generations would pass without anyone noticing a difference. There's something deeply peaceful about contemplating these cosmic timescales. Our daily worries and concerns, which can seem so overwhelming in the moment, fade into insignificance when viewed against the backdrop of planetary evolution. The deadline you're stressed about, the argument you had yesterday, the uncertainty about tomorrow, all of these are mere fleeting moments in a story that stretches across billions of years. And yet, paradoxically, this cosmic perspective also highlights how precious and unique each moment is. The fact that we're here at all, that Earth's orbit has remained stable enough for life to evolve and thrive, that we've developed the consciousness to contemplate these questions, is remarkable. We're the universe becoming aware of itself, using instruments made of atoms forged in ancient stars to study visitors from other star systems. In a very real sense, we're the cosmos investigating its own nature. The passage of 3I Atlas through our solar system lasted only a few months from our perspective. It appeared, brightened, fragmented, and then faded back into the darkness, continuing on its hyperbolic trajectory that will carry it back into interstellar space, never to return. By the time you wake up tomorrow, it will be millions of kilometers farther away, and distance that grows larger with each passing second. And yet, if the simulations are correct, its gravitational influence might echo through our solar system for millions of years to come. This is the beautiful paradox of gravitational interactions. The influence is instantaneous in one sense, the force acting across space at the speed of light. But the consequences unfold over geological, even astronomical timescales. It's like dropping a pebble in a vast, calm lake. The splash happens in an instant, but the ripples spread outward in perfect circles, eventually reaching the farthest shores long after the pebble has settled on the bottom. As we continue to track the planets with ever greater precision, we might eventually be able to detect the subtle signature of 3I Atlas's passage. Perhaps in a decade or a century, when our measurements have become even more precise, we'll be able to say with certainty, yes, this comet from another star shifted Earth's orbit by exactly this amount. Or perhaps we'll discover that its influence was even more subtle than we thought, lost in the noise of countless other small perturbations. Either way, the mere possibility that an interstellar visitor could leave such a mark on our solar system expands our understanding of our place in the cosmos. We're not isolated, we're not separate. We're part of a vast interconnected web of gravitational relationships that extends throughout the galaxy and beyond. Every star, every planet, every comet and asteroid, every grain of dust floating in space is connected to every other through the invisible threads of gravity. This interconnectedness extends through time as well as space. The current configuration of our solar system is the result of countless interactions over billions of years. Every asteroid that's ever passed by, every comet that's ever fallen toward the sun, every close encounter with another star as we orbit the galactic center, all of these have contributed to the precise arrangement we see today. And 3 Atlas is now part of that history, its influence woven into the fabric of our solar system's future evolution. There's a concept in chaos theory called sensitive dependence on initial conditions, sometimes known as the butterfly effect. The idea is that in certain systems, tiny changes in the starting conditions can lead to vastly different outcomes. The classic example is a butterfly flapping its wings in Brazil, potentially causing a tornado in Texas weeks later. The atmosphere is so complex, so interconnected, that tiny perturbations can amplify over time into major events. The solar system, with its multiple bodies all pulling on each other gravitationally, is exactly this kind of sensitive system. Over short timescales, a few years or decades or even centuries, the orbits of the planets are predictable, stable, almost clockwork-like. But over millions of years, tiny influences can accumulate and amplify. A gravitational nudge from a passing comet might shift a planet's orbit just enough to change how it interacts with other planets, which in turn changes their orbits, creating a cascade of effects that could ultimately reshape the entire solar system. This isn't cause for alarm though. These changes happen so slowly that they're imperceptible on human timescales. The Earth will continue its steady orbit around the Sun tomorrow, and the next day, and for millions of days to come. Seasons will change as they always have. The moon will rise and set. The familiar constellations will wheel overhead. From our limited human perspective, the cosmos appears eternal and unchanging. But knowing about these slow, subtle changes adds a layer of depth to our appreciation of the night sky. When you look up at the planets, you're not seeing static points of light fixed in eternal orbits. You're seeing a dynamic system in constant, if slow, evolution. Each planet is engaged in an intricate gravitational dance with all the others, a dance whose choreography is occasionally influenced by visitors from beyond. Mars, that red wanderer that has fascinated humanity for millennia, might have had its orbit shifted by a few meters when 3I Atlas passed by. Jupiter, the giant guardian of the inner solar system, might have felt a tiny tug that will echo through its orbit for millions of years. Saturn, with its beautiful rings, might have experienced the slightest change in its velocity, a change so small that our most sensitive instruments can barely detect it, but a change nonetheless. Even the outer planets, Neptune and Uranus, dwelling in the cold darkness at the edge of our solar system, might have been affected. The influence would have been incredibly tiny at such distances, but in the precise mathematics of orbital mechanics, even the smallest force matters. Over cosmic timescales, these tiny forces add up, like compound interest in a savings account that's been accumulating for billions of years. And what about Earth itself? Our precious blue marble, the only world we know of that harbours life, might now be on a slightly different trajectory through space because of this interstellar visitor. The change is so small that it won't affect the climate or the seasons or anything else that matters to life on Earth. But it's there, encoded in the mathematics of our orbit, a permanent reminder of our encounter with 3I Atlas. This brings us to a fascinating question that scientists are still grappling with. If interstellar objects like 3I Atlas can influence planetary orbits, how many such encounters have there been over the history of the solar system? And more intriguingly, What cumulative effect have they had? Could the current configuration of our solar system, the specific orbits and inclinations and eccentricities we observe, be partly the result of countless encounters with interstellar visitors over billions of years? We know that the early solar system was a chaotic place. Planets migrated inward and outward. Some may have been ejected entirely. The current, relatively stable configuration we see today is the result of billions of years of gravitational evolution. But perhaps interstellar visitors have played a larger role in this evolution than we previously thought. Perhaps they've been silent sculptors, their tiny gravitational chisels slowly reshaping the architecture of our cosmic neighborhood. The discovery of 3I Atlas and the two other confirmed interstellar objects before, it has opened our eyes to the fact that such visitors are probably much more common than we once believed. With improved detection systems, we're likely to discover many more in the coming years and decades. Each one will provide another data point, another piece of the puzzle, helping us understand how our solar system interacts with the wider galaxy. Some scientists have even suggested that interstellar objects might have played a role in delivering water and organic compounds to the early Earth. If comets from other star systems have been passing through our solar system for billions of years, some of them must have impacted Earth and the other planets. Could some of Earth's water have come from other star systems? Could some of the building blocks of life have been delivered by interstellar messengers? These are questions that would have seemed like pure science fiction just a few decades ago, but now they're serious scientific hypotheses. The study of 3I Atlas has also revealed something fascinating about the nature of comets themselves. As it approached the Sun and began to fragment, astronomers observed that it broke apart in a very particular way, different from how most solar system comets fragment. This suggests that its internal structure, the way its ice and dust were arranged, was different from our local comets. This makes sense when you consider that it formed in a completely different environment, around a different star under different conditions. Imagine the journey this comet has taken. It likely formed billions of years ago in the protoplanetary disk around a young star, perhaps one very different from our Sun. For millions of years it orbited that star along with other comets and asteroids and perhaps planets we'll never see. Then, through some gravitational interaction, perhaps a close encounter with a planet or another star, it was ejected from its home system and sent on a journey through interstellar space. For millions or perhaps billions of years, it drifted through the darkness between the stars. The temperature would have been close to absolute zero. No sunlight would have warmed its surface. It would have been exposed to cosmic rays and the hard radiation of space. And through all of this, it remained intact, a frozen time capsule carrying information about another star system. Then, by pure chance, its path intersected with our solar system. As it fell toward our Sun, it began to warm up for the first time in perhaps billions of years. The ices that had been frozen solid began to sublimate. Dust that had been locked in place began to drift away. And in those final months, as it rounded the Sun and headed back out into interstellar space, it gave us a brief glimpse of its nature, a fleeting opportunity to study a piece of another star system. The fact that it fragmented during this passage adds another layer to the story. Each fragment followed a slightly different path, each one interacting gravitationally with the planets in a slightly different way. It's as if the comet split itself into multiple messengers, each one carrying a slightly different gravitational message to the planets of our solar system. The combined effect of all these fragments is what scientists are now trying to calculate. There's something poetic about the fragmentation of 3I Atlas, this ancient object, which had survived billions of years in the frozen darkness of interstellar space, couldn't survive its encounter with our Sun. The very warmth that revealed its nature to us also destroyed it. It's a reminder of the violence that underlies the apparent serenity of space. Even in the vast emptiness, forces are at work that can create and destroy on scales we can barely imagine. As we contemplate these cosmic interactions, it's worth remembering that our solar system itself is moving through space. We're not stationary. the Sun and all its planets are orbiting the center of the Milky Way galaxy at a speed of about 220 kilometers per second. It takes us about 225 million years to complete one orbit, a period sometimes called a cosmic year. During each cosmic year, we pass through different regions of the galaxy, regions with different densities of stars and interstellar material. This means that the rate at which interstellar objects pass through our solar system probably varies over time. When we're passing through denser regions of the galaxy, we might see more visitors. When we're in emptier regions, they might be rarer. Right now, we happen to be in a relatively empty region called the local bubble, a cavity in the interstellar medium probably created by ancient supernovae. But this won't always be the case. In about 30,000 years, we'll be passing closer to the star Gliese 710, which will come within about a light-year of the Sun. This close passage will likely disturb the Oort cloud, the vast sphere of comets that surrounds our solar system, sending some of them falling toward the inner solar system. It's possible that Gliese 710 will also bring with it its own collection of comets and asteroids, some of which might pass through our solar system as interstellar visitors. These future encounters remind us that the story of 3I Atlas is not unique. It's part of an ongoing process, a continuous exchange of material and gravitational influence between star systems. We're all part of a galactic community, sharing space, sharing material, influencing each other in ways both obvious and subtle. The boundaries we draw around our solar system are somewhat artificial. In reality, we're part of a continuous, interconnected galactic ecosystem. The study of interstellar objects like 3I Atlas is also pushing the boundaries of our technology. To detect these objects, we need telescopes that can scan large areas of the sky quickly and repeatedly. We need sophisticated software that can identify moving objects against the background of stars. We need precise tracking systems that can follow these objects as they move through the solar system. And we need powerful computers to run the simulations that help us understand their gravitational influences. Each improvement in our technology reveals new aspects of these cosmic visitors. For example, spectroscopic observations of 3I Atlas revealed that it contained unusual amounts of certain compounds, suggesting it formed in an environment rich in carbon monoxide. This tells us something about the conditions around its parent star, information we could never have obtained any other way. It's like doing archaeology on a cosmic scale, piecing together the history of other star systems from the fragments that happened to pass our way. The fragmentation of 3I Atlas was particularly revealing. By studying how it broke apart, scientists could infer things about its internal structure. Was it a loosely bound rubble pile held together by weak forces, or was it a more solid object that broke under thermal stress? The way the fragments moved apart from each other, their relative sizes and velocities, all provided clues about the comet's composition and structure. This kind of detailed observation would have been impossible just a few decades ago. We're living in a golden age of astronomy, where our instruments are sensitive enough to detect and study objects that our predecessors could only dream about. Every year brings new discoveries, new insights, new questions about our place in the cosmos. And each discovery, like that of 3I Atlas, adds another piece to the vast puzzle of understanding our universe. As you drift deeper into relaxation, perhaps you can imagine yourself floating above the solar system, looking down at the sun and planets from a cosmic perspective. From this vantage point, you could see the planets as tiny dots of light, each following its prescribed path around the sun. You might see Earth, a pale blue dot, third from the sun, carrying all of humanity on its endless journey through space. Now imagine you could see the path of 3I Atlas, a long hyperbolic arc cutting through the plane of the solar system. You could see how it approached from below, rose up through the plane where the planets orbit, swung around the sun, and then departed in a different direction, heading back out into interstellar space. For just a brief moment in cosmic time, its path intersected with ours, creating a gravitational relationship that will persist long after the comet itself has disappeared into the darkness. From this cosmic perspective, you might also notice something else. The solar system isn't isolated. There are other stars nearby, and some with their own planetary systems, and between them all there's a constant flow of material, rocks and ice and dust, some of it bound to stars, some of it drifting free. 3i Atlas is just one participant in this cosmic exchange, one messenger among many. This view might also help you appreciate the incredible precision of planetary orbits. Despite all the gravitational influences, despite the constant tugs from passing asteroids and comets, despite the complex multi-body interactions, the planets continue their stable orbits year after year, century after century, millennium after millennium. It's a testament to the fundamental stability of our solar system, a stability that has allowed life to flourish on at least one world. But this stability isn't absolute, it's dynamic, constantly adjusting to new influences. Every passing asteroid, every visiting comet, every grain of interstellar dust that falls into the solar system adds its tiny contribution to the gravitational symphony. The orbits we see today are the sum of all these influences integrated over billions of years, and they'll continue to evolve, slowly and subtly, for billions of years to come. The story of 3i Atlas also connects to larger questions about planetary system formation and evolution throughout the galaxy. If interstellar objects can influence planetary orbits, then this must be happening in other star systems too. Young planetary systems, still in the process of formation, might be particularly susceptible to these influences. A large interstellar object passing through a protoplanetary disk could significantly affect how planets form and where they end up. This raises intriguing possibilities about the diversity of planetary systems in our galaxy. Perhaps some of the unusual exoplanet systems we've discovered, with planets in highly eccentric orbits or unusual configurations, are the result of encounters with interstellar visitors. Perhaps our own solar system's architecture, which seems relatively orderly compared to some exoplanet systems, is partly due to the specific history of interstellar encounters we've experienced. We're only just beginning to explore these connections. As we discover more exoplanet systems and more interstellar objects, we'll be able to build a more complete picture of how planetary systems evolve and interact. Each new discovery adds another data point, another piece of evidence that helps us understand the complex processes that shape worlds throughout the cosmos. The passage of 3i Atlas also reminds us of the role of chance in cosmic evolution. If this comet had passed through our solar system at a different time, when the planets were in different positions, the gravitational interactions would have been completely different. If it had approached from a different angle or at a different speed, the effects would have changed. The specific influence it had on our solar system is the result of a unique combination of factors that will never be repeated exactly. This element of randomness is humbling. It reminds us that despite all our scientific knowledge, despite our ability to predict and model, there are aspects of the universe that are fundamentally unpredictable. We can calculate probabilities, we can run simulations, we can make educated guesses, but we can't predict exactly when the next interstellar visitor will arrive or what effect it will have. And yet, this unpredictability is also what makes the universe so fascinating. If everything were perfectly predictable, if we could calculate every future event with absolute certainty, the cosmos would lose much of its wonder. The fact that surprises like 3i Atlas can still occur, that we can still be amazed by unexpected discoveries, keeps science vibrant and exciting. As we move deeper into the 21st century, our ability to detect and study interstellar objects will only improve. New telescopes are being built that will be able to scan the entire sky every few nights, catching objects that might otherwise slip by unnoticed. Space missions are being planned that could potentially intercept and study interstellar visitors up close. Imagine a spacecraft rendezvousing with an object from another star system, studying it in detail, perhaps even returning samples to Earth. Such missions would revolutionize our understanding of other star systems. Instead of studying them from afar with telescopes, we could examine actual pieces of them, materials that formed around other stars under different conditions. We could test our theories about planetary formation, about the distribution of elements in the galaxy, about the processes that shape worlds throughout the cosmos. The story of Three-Eye Atlas is also a reminder of how much we still don't know. Despite all our advances, despite our sophisticated instruments and powerful computers, we're still in the early stages of understanding our cosmic neighborhood. Every discovery raises new questions, reveals new mysteries, opens new avenues for exploration. We're like children on a beach, playing with pebbles while an entire ocean of knowledge stretches out before us. Consider, for instance, the question of where Three-Eye Atlas came from. We know it came from interstellar space, but from which star system? How long ago was it ejected? What caused its ejection? These are questions we may never be able to answer definitively. The comet has been traveling for so long, and space is so vast, that tracing its path back to a specific star is virtually impossible with our current technology. But perhaps future generations will develop techniques we can't even imagine today. Perhaps they'll be able to analyze the trajectories of thousands of interstellar objects and trace them back to their origins, mapping the flow of material between star systems throughout our region of the galaxy. Perhaps they'll discover that certain stars are prolific producers of interstellar objects while others retain most of their material. Perhaps they'll find patterns we haven't even thought to look for. The gravitational influence of Three-Eye Atlas on our solar system, if it exists, is part of this larger story of cosmic evolution. Every small perturbation, every tiny change in a planet's orbit, contributes to the long-term evolution of the system. Over millions and billions of years, these small changes accumulate, potentially leading to significant reconfigurations. It's a slow process, almost incomprehensibly slow from our human perspective, but inexorable. This long-term perspective can be oddly comforting. Yes, change is constant, even on cosmic scales, but it happens so slowly that life has time to adapt. The Earth has experienced massive changes over its history, from global ice ages to periods of extreme heat, from asteroid impacts to volcanic catastrophes, and yet life has persisted and thrived. The potential orbital changes from interstellar visitors are tiny compared to these other influences, gentle nudges rather than catastrophic disruptions. As you continue to relax, letting these cosmic thoughts wash over you like gentle waves, consider how remarkable it is that we can even contemplate these questions. A collection of atoms that originated in the hearts of dying stars has organized itself into a form capable of understanding its own origins. We are literally stardust that has become conscious, able to look up at the night sky and recognize our kinship with everything we see. The story of Three-Eye Atlas is our story too, in a way. We're all travelers through space, all of us riding on this planet as it orbits the sun, as the sun orbits the galaxy, as the galaxy moves through the universe. We're all subject to the same gravitational forces, the same physical laws, the same cosmic processes. The comet may have come from another star system, but it's made of the same fundamental particles as we are, obeying the same laws of physics, participating in the same cosmic dance. In the grand tapestry of the universe, Three Atlas represents a single thread, briefly visible as it passed through our region of space, now fading back into the darkness. But its passage has added to the pattern, contributed to the ongoing weaving of cosmic history. And we, in our brief moment of consciousness, have been privileged to witness it, to study it, to add its story to our growing understanding of the cosmos. The possibility that this interstellar visitor might have shifted planetary orbits, even by the tiniest amount, connects us to the larger galaxy in a tangible way. We're not isolated observers of the cosmos, we're participants in it. Every star we see in the night sky exerts a gravitational influence on us, however tiny. Every cosmic ray that passes through our bodies connects us to distant cosmic events. We're embedded in the universe, inseparable from it, shaped by it even as we seek to understand it. This interconnectedness extends beyond just physical influences. The atoms in your body, the calcium in your bones, the iron in your blood, the carbon in your DNA. All of these were forged in the nuclear furnaces of stars that died billions of years ago. You are, quite literally, made of cosmic material. The water in your body may have been delivered to Earth by comets, possibly even interstellar comets like 3I Atlas. You're a collection of cosmic history, a living archive of stellar evolution. As we prepare to journey deeper into the mysteries of space and time, let's carry with us this sense of connection, this awareness that we're part of something vast and beautiful and still largely mysterious. The story of 3I Atlas is just one chapter in an ongoing cosmic narrative, a narrative in which we all play a part. Whether its passage truly shifted planetary orbits or not, it has certainly shifted our perspective, reminding us of our place in the grand celestial dance. The night continues around us, filled with invisible wonders. Right now, as you rest, other interstellar objects might be passing through our solar system, too faint for our telescopes to detect. Gravitational waves from distant cosmic events are passing through your body. Neutrinos from the sun and from distant supernovae are streaming through you by the billions. You're immersed in a sea of cosmic phenomena, most of it invisible, all of it connecting you to the wider universe. And somewhere out there, 3I Atlas continues its journey. Having passed through our solar system, having possibly left its subtle gravitational signature on our planets, it now heads back into the vast emptiness between the stars. It will travel for millions of years before it encounters another star system, if it ever does. It carries with it, frozen in its remaining fragments, information about both its original home and its brief encounter with our sun. It's a cosmic messenger, a bridge between star systems, a reminder that we're all part of the same galactic community. As we transition into contemplating the vast ocean of space that surrounds us, remember that every point of light in the night sky has its own story, its own collection of worlds, its own history of cosmic encounters. The universe is full of such stories, most of them unknown to us, all of them part of the grand narrative of cosmic evolution. And we, on our small blue world, orbiting an ordinary star, have developed the remarkable ability to read some of these stories, to understand our place in the cosmic order, to wonder at the beauty and complexity of it all. The great ocean of space stretches out before us, vast and dark and full of wonders we're only beginning to discover. Like ancient mariners setting out to explore Earth's oceans, we're at the beginning of a great age of cosmic exploration. Every new discovery, every visiting comet, every detected gravitational wave adds to our maps of this vast ocean. And just as Earth's oceans connect all continents, the ocean of space connects all star systems, all galaxies, all corners of the observable universe. In this cosmic ocean, waves of gravity ripple outward from every massive object, creating interference patterns of incredible complexity. These gravitational waves, predicted by Einstein and recently detected by our most sensitive instruments, carry information about cosmic events across billions of light years. When two black holes merge in a distant galaxy, the gravitational waves from that event eventually wash over Earth, slightly stretching and compressing space itself as they pass. We are literally bathed in these cosmic ripples, these whispers from distant corners of the universe. The ocean of space is not empty, as was once thought. It's filled with a thin soup of particles and fields, dark matter and dark energy, magnetic fields and cosmic rays. It's a dynamic, ever-changing medium through which planets and stars and galaxies move. And through this ocean, objects like 3I Atlas sail like cosmic ships, carried by the currents of gravity and momentum, occasionally making port in star systems before continuing their endless voyages. Think of space not as a void, but as an ocean of possibility. Every cubic meter of space, even the emptiest regions between galaxies, contains virtual particles popping into and out of existence, quantum fields fluctuating, gravitational waves passing through. It's a seething sea of activity at the quantum level, even in places that appear perfectly empty to our instruments. This quantum foam, as physicists sometimes call it, underlies all of reality, connecting everything to everything else at the most fundamental level. In this ocean, our solar system is like a small archipelago of islands, held together by the gravity of our sun. Earth is just one island in this chain, a particularly beautiful one with its blue oceans and white clouds, but still just one small part of a larger system. And this system itself is just one of billions in our galaxy, which is one of trillions in the observable universe. The scale is so vast that our minds struggle to comprehend it, and yet somehow we're beginning to map it, to understand it, to see our place within it. The passage of 3 Atlas through our solar system is like a message in a bottle, thrown from a distant shore and washing up on our cosmic beach. We don't know who sent it or why. We can't read the full message, but its mere existence tells us something important. We're not alone in this ocean. Other shores exist, other islands of matter and energy around other stars, and occasionally material from those distant shores reaches us, carrying information about places we may never directly visit. As we drift deeper into contemplation of this cosmic ocean, we begin to understand that the boundaries we perceive, the divisions between solar systems, between galaxies, even between us and the cosmos, are somewhat artificial. In reality, everything is connected through fields and forces that extend infinitely through space. The gravity of every atom in your body extends throughout the entire universe, growing weaker with distance but never quite reaching zero. You're gravitationally connected to every star you see and every star you don't see, to every planet, every comet, every grain of cosmic dust. This interconnectedness means that the influence of 3I Atlas on our solar system, however small, is just one example of a universal principle. Everything influences everything else. Every movement, every change sends ripples through the fabric of space-time that eventually reach the farthest corners of the cosmos. It's a beautiful thought that we're all part of this cosmic web, all influencing each other in ways both obvious and subtle, all participating in the grand dance of the universe. The ocean of space also has its currents and tides, though they operate on scales difficult for us to perceive. The solar system is currently moving through a region called the local interstellar cloud, a slightly denser area of gas and dust about 30 light-years across. We entered this cloud perhaps 10,000 years ago, and will remain within it for another 10,000 to 20,000 years. This cloud affects the boundary of our solar system, the heliopause where the solar wind meets the interstellar medium, creating a complex and dynamic interface between our sun's influence and the wider galaxy. Beyond the local interstellar cloud, we're part of a larger structure called the local bubble, a region of relatively empty space about 300 light-years across. This bubble was likely created by supernovae that exploded millions of years ago, clearing out the interstellar medium and creating a cosmic cavity. We live inside this bubble, protected somewhat from the denser regions of the galaxy, but this hasn't always been the case, and won't always be in the future. As our solar system orbits the galactic center, we pass through different regions with different densities, different populations of stars, different levels of radiation. These passages affect the rate at which interstellar objects like 3I Atlas visit us. They affect the cosmic ray flux that reaches Earth. They might even affect the stability of the Oort cloud, potentially sending comets into the inner solar system. We're not just moving through space, we're moving through a complex, structured, dynamic environment that influences us in countless ways. The ocean of space is also filled with waves of light, electromagnetic radiation spanning an incredible range of wavelengths. From radio waves longer than planets to gamma rays with wavelengths smaller than atomic nuclei, this radiation carries information about cosmic events throughout the universe. The light from distant galaxies tells us about the history of the cosmos. The cosmic microwave background radiation, the afterglow of the Big Bang, still fills all of space, a faint echo of the universe's violent birth. When 3I Atlas passed through our solar system, it was bathed in sunlight for perhaps the first time in billions of years. The photons from our sun, carrying energy generated by nuclear fusion in the sun's core, warmed the comet's surface, causing ices to sublimate and creating the coma and tail that made it visible to our telescopes. For a brief moment, our sun illuminated this visitor from another star, allowing us to study it, to learn from it, to add its story to our growing understanding of the cosmos. But the ocean of space is also dark, darker than we once imagined. We now know that ordinary matter, the stuff that makes up stars and planets and comets and us, represents only about 5% of the universe. The rest is dark matter and dark energy, mysterious components that we can detect only through their gravitational effects. This dark ocean surrounds us, pervades us, influences us in ways we're only beginning to understand. Every galaxy, including our own, is embedded in a vast halo of dark matter, invisible but undeniably present. The gravitational influence of this dark matter affects everything, including the orbits of planets and the trajectories of interstellar objects. When we calculate whether 3I Atlas might have shifted planetary orbits, we have to account not just for the visible matter, but also for this invisible dark component. It's like trying to understand ocean currents while only being able to see the surface waves. Knowing that deeper currents, invisible but powerful, shape the overall flow. In this dark ocean, 3I Atlas was like a phosphorescent creature, briefly glowing as it passed through our region of space. Its fragmentation created multiple glowing pieces, each following its own path, each telling part of the story. And then, as quickly as it appeared, it faded back into the darkness, returning to the vast emptiness between the stars. But its passage left ripples, gravitational influences that continue to propagate through our solar system, subtle but real. The ocean of space is ancient, nearly 14 billion years old, and yet it's still young in cosmic terms. Stars are still forming, planets are still coalescing from cosmic dust. Life is still evolving on countless worlds we haven't yet discovered. The universe is still in its youth, with trillions of years of evolution ahead of it. The current era, when stars shine and planets orbit and life can exist, is just a brief chapter in the much longer story of the cosmos. In this ancient ocean, our solar system is relatively young at just 4.6 billion years old. We formed from a cloud of gas and dust enriched by previous generations of stars, inheriting heavy elements forged in stellar cores and supernovae. The atoms that make up Earth, that make up you, have been on incredible journeys through this cosmic ocean, passing through multiple stars, drifting through interstellar space, finally coming together to form our world and everything on it. 3I Atlas, too, is a product of this cosmic recycling. The materials that made it up were once part of an interstellar cloud that collapsed to form a star and its surrounding disk. In that disk, ices and dust came together to form comets and asteroids and perhaps planets. And then, through some cosmic accident, this particular comet was ejected, sent on a journey that would eventually bring it through our solar system. It's a reminder that nothing in the universe is truly isolated. Everything is part of larger cycles of creation and destruction, formation and dispersal. The ocean of space is also an ocean of time. When we look out into space, we look back in time. The light from the nearest star takes over 4 years to reach us. The light from the center of our galaxy takes 26,000 years. The light from the most distant galaxies has been traveling for over 13 billion years. We see the universe not as it is, but as it was. We're surrounded by the past, by light and gravitational waves and cosmic rays that have been traveling through the ocean of space for eons. This means that when we detected 3I Atlas, we were seeing it as it was minutes or hours earlier, depending on its distance. Its light had to travel across the ocean of space to reach our telescopes, and if its passage really did shift planetary orbits, those gravitational influences propagated outward at the speed of light, reaching each planet at a slightly different time. It's a reminder that even gravity, which seems instantaneous, actually propagates through space at a finite speed, creating ripples in the fabric of space-time itself. In the vast ocean of space, distance and time become interchangeable. We measure cosmic distances in light years, the distance light travels in a year. But this also means we're measuring time, the time it takes for information to travel from one place to another. When we say a star is 100 light years away, we're also saying we see it as it was 100 years ago. The ocean of space is thus also an ocean of history, with every distant object showing us a different moment in cosmic time. As you float in this contemplation, imagine yourself as a cosmic navigator, charting courses through this vast ocean. Your ship is the Earth, steadily sailing around the sun. Your charts are the constellations, the patterns of stars that have guided navigators for millennia. And occasionally you encounter other vessels like 3i Atlas, ships from distant ports, carrying cargo from other star systems, briefly sharing the same waters before continuing on their separate journeys. The ocean of space has its safe harbours and its dangerous waters. The habitable zone around a star where liquid water can exist on a planet's surface is like a safe harbour where life can flourish. Too close to the star and water boils away, too far and it freezes solid. Earth sits comfortably in this zone, our cosmic harbour, protected by our atmosphere and magnetic field from the harsh radiation of space. But even in this safe harbour, we're not completely isolated from the ocean around us. Cosmic rays penetrate our atmosphere. Meteorites fall from the sky. The solar wind interacts with our magnetic field, creating the aurora. And occasionally, an interstellar visitor like 3i Atlas passes through, reminding us that we're part of a larger ocean. Subject to its currents and tides, its visitors and influences. The ocean of space is also filled with islands of matter, from tiny dust grains to massive galaxy clusters. Each island has its own story, its own history of formation and evolution. Some islands are active, with ongoing star formation and dynamic processes. Others are quiet, their stars old and stable, their planets locked in ancient orbits. Our solar system is somewhere in between, stable enough for life to evolve but still dynamic enough for change and evolution. In this ocean, comets like 3i Atlas are like seeds, carrying the potential for new chemistry, perhaps even new life, from one island to another. Scientists have long speculated about panspermia, the idea that life might spread through the universe via comets and asteroids. While we have no evidence that 3i Atlas carried any form of life, the possibility remains that some interstellar visitors might be carrying organic compounds or even microorganisms from other star systems. The ocean of space is transparent to some things and opaque to others. Light travels freely through empty space, allowing us to see distant galaxies. But the universe is opaque to certain wavelengths, absorbed by dust and gas. It's also opaque to neutrinos from the early universe, these ghostly particles that barely interact with matter. And it might be opaque to other things we haven't yet discovered, dark matter particles or exotic forms of radiation that we don't yet know how to detect. This selective transparency means that our view of the cosmic ocean is limited, like trying to understand Earth's oceans by only looking at the surface. We're developing new instruments, new techniques, to peer deeper into this ocean, to see things that were previously invisible. Each new window we open reveals new wonders, new mysteries, new questions about the nature of the cosmos. The passage of 3i Atlas through our solar system opened a small window into the nature of other star systems. By studying its composition, we learned something about the conditions where it formed. By tracking its trajectory, we learned something about the dynamics of our galaxy. By considering its gravitational influence, we're learning something about the sensitivity of planetary orbits to small perturbations. Each piece of information adds to our understanding of the cosmic ocean in which we sail. As we drift deeper into this contemplation, we begin to see that the ocean of space is not just a physical reality, but also a metaphor for the vastness of what we don't know. We've mapped only a tiny fraction of this ocean. We've visited, with our spacecraft, only a few nearby islands. We've detected only a handful of the countless interstellar objects that must pass through our solar system. We're like ancient Polynesian navigators, having discovered a few islands but knowing that vast unexplored waters stretch out in all directions. And yet, like those ancient navigators, we're learning to read the signs, to understand the currents and winds of space. We're learning to predict where planets will be, where comets will appear, when eclipses will occur. We're beginning to understand the large-scale structure of the universe, the cosmic web of galaxies and dark matter that gives shape to the ocean of space. We're even beginning to detect the gravitational waves that ripple through this ocean, carrying information about distant cosmic events. The story of Three-Eye Atlas is just one note in this vast cosmic symphony, one ripple in this infinite ocean. But it's a note that we happen to hear, a ripple that we happen to detect, and from this single observation, we're extracting as much information as we can, trying to understand not just this one comet, but what it tells us about the nature of the cosmic ocean itself. As you continue to relax, to drift deeper into this peaceful contemplation, remember that you too are part of this ocean. The atoms in your body have sailed through it for billions of years. The energy that powers your thoughts comes ultimately from the sun, a star that itself is sailing through the galaxy. You're not separate from the cosmic ocean. You're a part of it. A temporary arrangement of matter and energy that has become conscious, able to contemplate its own existence and its place in the vastness of space. The ocean of space will continue long after we're gone, long after Earth itself is gone, long after the sun has died. New stars will form, new planets will coalesce, new comets will sail between star systems. The ocean is eternal, or at least so vast in time and space that it might as well be eternal from our limited perspective. And throughout this vast future, the ripples from every event, including the passage of Three-Eye Atlas through our solar system, will continue to propagate, becoming ever fainter but never quite disappearing. In this ocean, nothing is ever truly lost. The information about every event encoded in gravitational waves and electromagnetic radiation and the motion of particles spreads outward through space and time. Somewhere in the universe, the light reflected from Three-Eye Atlas when it passed through our solar system is still traveling outward, carrying information about this cosmic encounter to distant corners of the galaxy. We're all leaving traces in the cosmic ocean, ripples that will outlast us by billions of years. As we prepare to focus more closely on Three-Eye Atlas itself, on this specific visitor from beyond, remember that it represents something larger. It's a messenger from the cosmic ocean, a reminder of the vastness that surrounds us, a bridge between our small island of light and warmth and the infinite darkness that stretches in all directions. Its story is our story, the story of matter and energy moving through space and time, occasionally coming together in interesting ways, creating moments of beauty and wonder in the vast cosmic night. Now, let's turn our attention to this specific visitor, this fragment of another star system that briefly graced our skies. Let's explore where it might have come from, what it's made of, and what its journey through our solar system tells us about the nature of cosmic wanderers. For in understanding Three-Eye Atlas, we're understanding something fundamental about the universe itself, about the constant exchange of matter and energy that connects all things in the vast ocean of space. From the deep darkness beyond Neptune, beyond the Kuiper Belt, beyond even the vast Oort cloud that marks the outer boundary of our sun's gravitational dominion, something ancient was approaching. It had been travelling for so long that if we could compress its journey into a single human lifetime, our entire recorded history would flash by in less than a second. This was 3i Atlas, though of course it had no name during its millions of years of silent travel through the void. It was simply a piece of cosmic debris, a frozen fragment of a distant star system, following the inexorable laws of physics through the emptiness between the stars. To understand this visitor, we must first appreciate the sheer improbability of its discovery. Space is so vast, so empty, that the chances of an object from another star system passing close enough to the Sun for us to detect it are infinitesimally small. If you were to scale down the universe so that the Sun was the size of a grain of sand, the nearest star would be another grain of sand about 4 miles away. And between them, nothing but emptiness. For 3i Atlas to have passed through our solar system at just the right time for us to detect it with our telescopes is a cosmic coincidence of extraordinary proportions. The comet itself was probably born in circumstances not too different from those that created the comets in our own solar system. Billions of years ago, around a star we'll never identify, a disk of gas and dust was slowly condensing into planets. In the outer reaches of this disk, where temperatures were cold enough for water and other volatiles to freeze, countless small bodies were forming. These were the comets and asteroids of that distant system, the leftover building blocks that didn't get incorporated into planets. But something happened to 3i Atlas that doesn't happen to most comets. Perhaps it passed too close to a giant planet and was gravitationally ejected from its home system. Perhaps its star had a close encounter with another star, disrupting the orbits of many small bodies. Perhaps the star died, exploding as a supernova or slowly expanding as a red giant, releasing its comets into interstellar space. We'll never know the exact mechanism, but somehow this particular comet was set free, sent on a journey that would last millions or billions of years. During its long voyage through interstellar space, 3i Atlas would have experienced conditions unlike anything in our solar system. The temperature would have been just a few degrees above absolute zero, cold enough that even hydrogen would be close to freezing. There would have been no sunlight to warm it, no solar wind to erode it, just the endless cold and darkness of the void. Cosmic rays, high-energy particles from distant supernovae and other violent events would have bombarded it constantly, slowly altering its surface chemistry, creating complex organic molecules in its ice. The comet would have been moving at a velocity of perhaps 20 to 30 kilometers per second relative to the average motion of stars in our galaxy. This might seem fast, but at this speed, it would take over 40,000 years to travel a single light year. The journey from its home star to our solar system might have taken millions of years, perhaps tens of millions, possibly even longer. During all this time, it was alone, a tiny island of matter in an ocean of emptiness, carrying within its frozen heart the chemical signature of another star system. We can imagine 3i Atlas slowly tumbling through space, rotating perhaps once every few hours or days, its irregular surface alternately facing different directions as it moved through the darkness. Without any forces acting on it except the gentle tug of distant stars, its rotation would have remained constant for millions of years. It's a kind of cosmic isolation that's difficult for us to comprehend. This object spinning silently in the void, no change, no events, just the slow passage of time marked only by its rotation and its gradual progress through space. Then, perhaps a few thousand years ago in cosmic terms, basically yesterday, something began to change. The comet began to feel, ever so slightly, the gravitational pull of our sun. At first, this pull would have been imperceptible, less than the gravitational attraction of a dust grain a meter away. But as 3i Atlas continued its approach, the sun's gravity grew stronger, beginning to curve its trajectory, pulling it inward from the darkness. This is where the story becomes particularly interesting from a scientific perspective. You see, when an object approaches from interstellar space, it's moving so fast relative to our solar system that the sun's gravity can't capture it. Instead, it follows a hyperbolic trajectory, swooping in toward the sun, gaining speed as it falls inward. then swinging around and heading back out into space, never to return. It's like a marble rolling quickly past a depression in the ground, dipping down briefly but having too much speed to be captured. As 3I Atlas fell toward the Sun, it began to warm up for the first time in perhaps billions of years. The ices that had been frozen solid since its formation began to feel the Sun's heat. At first, nothing visible happened. The comet was still too cold, too far from the Sun. But as it crossed the orbit of Jupiter, then Mars, the heating became significant. The surface temperature rose from near absolute zero to hundreds of degrees Kelvin. For an object that had been frozen for so long, this was a dramatic change. This is when 3I Atlas transformed from an invisible chunk of ice and rock into a visible comet. The heat from the Sun caused the ices to sublimate, turning directly from solid to gas. This gas, along with dust that had been trapped in the ice, formed a cloud around the comet's nucleus called a coma. The solar wind and radiation pressure from the Sun then pushed this material away, creating the characteristic tail that makes comets so spectacular. But 3 Atlas was different from most comets we observe. Its composition, revealed through spectroscopic analysis of the light reflected and emitted by its coma, showed unusual ratios of different compounds. There was more carbon monoxide than we typically see in solar system comets, suggesting formation in a colder environment or around a star with different characteristics than our Sun. The dust particles were also different, with sizes and compositions that told a story of formation under alien conditions. As astronomers around the world trained their telescopes on this interstellar visitor, they noticed something troubling and fascinating. The comet was brightening more slowly than expected, and its coma seemed irregular. Then, in March and April of 2020, it became clear what was happening. 3I Atlas was fragmenting, breaking apart into multiple pieces. This wasn't entirely unexpected. Many comets fragment as they approach the Sun. The thermal stress of heating, combined with the comet's rotation and the tidal forces from the Sun's gravity, can tear these fragile objects apart. But for 3I Atlas, fragmentation meant something special. This was our only chance to study an interstellar comet up close, and it was disintegrating before our eyes. Each fragment provided a window into the comet's interior, revealing materials that had been protected from cosmic rays during its long interstellar journey. It was like watching an ancient artifact break open, revealing treasures that had been hidden for eons. The fragmentation also complicated any calculation of the comet's gravitational influence on the planets. Instead of a single mass following a single trajectory, we now had multiple fragments, each with its own slightly different path. Some fragments were moving faster than others. Some were pushed more strongly by solar radiation. The gravitational influence of the original comet was now distributed among these pieces, creating a more complex pattern of perturbations. Through spectroscopic analysis, scientists detected water, carbon monoxide, carbon dioxide, and various organic compounds in the comet's coma. These are the same basic ingredients we see in solar system comets, confirming that the basic chemistry of planetary system formation is similar throughout the galaxy, but the specific ratios, the isotopic signatures, the trace elements, all of these were subtly different, bearing witness to formation under different conditions. One of the most intriguing aspects of 3I Atlas was its size. Based on its brightness and the amount of material it was shedding, astronomers estimated that the original nucleus was perhaps a few kilometers across, maybe 5 or 10 at most. This might seem large, but remember, this object had survived a journey of millions of years through interstellar space. It had endured cosmic ray bombardment, the gravitational tugs of passing stars, the slow erosion of volatile materials. The fact that it was still several kilometers across when it reached us suggests it might have been much larger when it began its journey. The trajectory of 3I Atlas through our solar system was carefully mapped using observations from telescopes around the world. It approached from the direction of the constellation Cassiopeia, diving down from above the plane where the planets orbit. It passed closest to the Sun on May 31st, 2020, coming within about 37 million kilometers, closer than Mercury's orbit. At this point, it was moving at over 70 kilometers per second relative to the Sun, fast enough to escape the solar system entirely. As it swung around the Sun, 3 Atlas passed relatively close to several planets. It came within about 150 million kilometers of Earth, roughly the same as the distance from Earth to the Sun. It passed even closer to Mars within about 100 million kilometers. These might seem like vast distances, and they are, but in terms of gravitational interactions, they're close enough for measurable effects, at least in principle. The fragmentation of the comet created what astronomers call a debris train, a line of fragments spread out along the comet's orbit. Some of these fragments were substantial, perhaps hundreds of meters across. Others were tiny, no bigger than dust grains. Each fragment continued to sublimate, creating its own small coma, its own contribution to the overall display. From Earth, the comet looked like a string of pearls, each pearl glowing with its own light. This fragmentation process revealed something important about the comet's structure. It wasn't a solid chunk of ice and rock, but rather a loosely bound collection of smaller pieces, what astronomers call a rubble pile. This structure is common among comets and asteroids, held together by weak forces, easily disrupted by thermal stress or tidal forces. The fact that an interstellar comet had this same structure suggests that the processes that form such objects are universal. As 3 Atlas rounded the Sun and began its journey back into interstellar space, it continued to fragment and sublimate. By the time it passed Earth's orbit again on its way out, it had lost a significant fraction of its mass. The material it shed, the gas and dust released from its nucleus, didn't just disappear. It became part of the inner solar system, eventually to be swept up by the planets or blown out by the solar wind. In a very real sense, part of 3I Atlas is still with us, its atoms now part of our solar system. This study of 3I Atlas also revealed something about the population of interstellar objects in our galaxy. Based on the detection of just a few such objects, astronomers can estimate how many must be passing through undetected. The numbers are staggering. There might be trillions of interstellar comets and asteroids in our galaxy, a vast population of cosmic wanderers moving between the stars. At any given moment, there might be thousands passing through our solar system, most too small or too distant to detect. This realization has profound implications for our understanding of planetary system formation and evolution. If trillions of objects have been ejected from their home systems, then the process of planetary formation must be incredibly wasteful, with far more material expelled than retained. It also means that star systems aren't isolated. They're constantly exchanging material, albeit at a very low rate. Over billions of years, this exchange could have significant effects. The chemical analysis of 3I Atlas provided hints about its origin. The high abundance of carbon monoxide suggested formation in a very cold environment, perhaps in the outer regions of its original system, or around a star cooler than our Sun. The presence of certain organic molecules suggested a rich chemistry, possibly enhanced by cosmic ray bombardment during its interstellar journey. Every molecule detected was a clue, a piece of evidence about conditions in another star system. One of the most fascinating aspects of studying 3I Atlas was comparing it to the 2 other confirmed interstellar objects we've detected. The first, 1E Oumuamua, discovered in 2017, was very different. It showed no cometary activity, appeared to be elongated or disc-shaped, and exhibited a mysterious acceleration that couldn't be explained by gravity alone. The second, 2I Borisov, discovered in 2019, was more comet-like but still had its unique characteristics. Each of these objects tells a different story about the diversity of interstellar visitors. The differences between these objects suggest that the population of interstellar wanderers is incredibly diverse. Some, like 3I Atlas and 2I Borisov, are clearly comets, rich in volatile ices. Others, like Oumuamua, might be rocky asteroids or something else entirely. This diversity reflects the variety of processes that can eject objects from star systems and the different conditions under which these objects formed. As 3I Atlas faded from view, heading back into the darkness from which it came, it left astronomers with more questions than answers. Where exactly did it come from? How old was it? What percentage of its original mass did it lose during its passage through our solar system? Could its gravitational influence really have shifted planetary orbits even slightly? These questions will drive research for years to come. The legacy of 3I Atlas extends beyond just scientific data. It has changed how we think about our solar system and its relationship to the galaxy. We now know that interstellar visitors are relatively common, that our solar system is regularly penetrated by objects from other stars. This knowledge adds a new dimension to our understanding of Earth's history. How many times over the past 4.6 billion years has an interstellar object passed through our solar system? Have any of them impacted Earth or other planets? Some scientists have suggested that interstellar objects might have played a role in delivering water or organic molecules to the early Earth. If comets from other star systems have been passing through our solar system for billions of years, some of them must have impacted our planet. The water in Earth's oceans, the organic molecules that became the building blocks of life, some of these might have come from other star systems, delivered by cosmic messengers like 3I Atlas. This possibility adds another layer to our cosmic connection. Not only are we made of stardust, atoms forged in the hearts of dying stars, but we might also contain molecules that formed around other stars, that travelled through interstellar space for millions of years before becoming part of our world. Every glass of water you drink might contain a few molecules that originated in another star system. Every breath you take might include atoms that have journeyed across the galaxy. The study of 3I Atlas has also spurred technological development. To better detect and study future interstellar visitors, astronomers are developing new telescopes and detection systems. The Vera Rubin Observatory, currently under construction, will survey the entire visible sky every few nights, capable of detecting objects much fainter than current telescopes can see. This will likely lead to the discovery of many more interstellar objects, each one adding to our understanding of the galaxy. There are even proposals for missions to intercept future interstellar visitors. Imagine a spacecraft waiting in the outer solar system, ready to race toward any interstellar object that passes through. Such a mission could study these visitors up close, perhaps even returning samples to Earth. This would revolutionize our understanding of other star systems, giving us actual pieces of them to study in our laboratories. The fragmentation of 3I Atlas, while disappointing in some ways, actually provided unique scientific opportunities. By breaking apart, the comet revealed its interior, showing us materials that had been shielded from cosmic rays and solar heating. Each fragment was like a core sample from the original body, preserving information about conditions when and where it formed. The way it fragmented, the sizes and velocities of the pieces, all provided clues about its structure and composition. As we've studied the trajectory of 3I Atlas and its fragments, we've had to account for many forces beyond just gravity. Solar radiation pressure pushed on the comet's dust particles. The solar wind, a stream of charged particles from the sun, interacted with the comet's gas. The uneven heating of the rotating nucleus created jet forces as gas escaped from the sunward side. All of these non-gravitational forces had to be modelled to understand the comet's precise path through our solar system. This complex modelling has improved our ability to predict the motion of all small bodies in the solar system. The techniques developed to study 3I Atlas are now being applied to potentially hazardous asteroids, improving our ability to predict whether they might impact Earth. In this way, the study of an interstellar visitor has practical applications for planetary defense, helping us better protect our world from cosmic impacts. The story of 3i Atlas also highlights the importance of international cooperation in astronomy. Observers from around the world contributed to tracking this comet. Data was shared freely among scientists regardless of nationality. This comet belonged to no country. It was a visitor to all of humanity, and humanity came together to study it. In our divided world, astronomy remains a unifying force, reminding us that we all share the same sky, the same cosmic heritage. As 3 Atlas continues its journey back into interstellar space, it carries with it some changes from its encounter with our Sun. It's now less massive, having lost material to sublimation. Its fragments are following slightly different trajectories, spreading out over time. The solar encounter has altered its rotation, its surface composition, its internal structure. It's no longer the same object that approached our solar system. In a sense, our Sun has left its mark on this interstellar wanderer, just as the wanderer might have left its mark on our planetary orbits. The comet will now travel for millions more years before it encounters another star system, if it ever does. By then, its fragments will have spread far apart, each one a separate messenger carrying information about both its original star system and its encounter with ours. Perhaps billions of years from now, one of these fragments will pass through another planetary system where intelligent beings will detect it, study it, and wonder about its history, just as we've wondered about 3 Atlas. This is the beautiful continuity of cosmic evolution. Objects form, travel, interact, fragment, and disperse, but the atoms themselves are eternal, or at least as eternal as anything can be in our universe. The atoms that made up 3i Atlas have existed since the early universe, passing through generations of stars, and they'll continue to exist long after our Sun has died. They're on an eternal journey through space and time, occasionally coming together in interesting configurations like comets or planets, or living beings, then dispersing again to continue their cosmic voyage. As we contemplate this visitor from beyond, we're reminded of our own cosmic journey. Earth itself is a traveller through space, carrying all of us on a voyage around the Sun, around the galaxy, through the universe. We're not stationary observers of cosmic events, we're participants in them. The passage of 3i Atlas through our solar system wasn't just something that happened out there in space. It was an event in which we were involved, however peripherally. The possibility that 3i Atlas might have shifted planetary orbits, even infinitesimally, connects us directly to this cosmic visitor. If Earth's orbit has changed, even by a meter, then every future sunrise, every future season, every future moment in Earth's history has been subtly influenced by this interstellar comet. We are now and forever part of each other's stories, linked by the invisible threads of gravity across the vast distances of space. The whispers of gravity surround us always, though we rarely pause to notice them. Right now, as you rest there in the darkness, you're falling. Not dramatically, not obviously, but falling nonetheless. You're falling toward the center of the Earth, pulled by every atom of our planet, and only the resistance of whatever surface supports you prevents you from continuing that fall. At the same time, you're falling toward the Moon, toward the Sun, toward every planet in our solar system, toward every star you can see, and every star you cannot see. Every massive object in the universe is pulling on you right now, and you're pulling back on each of them with exactly the same force. This is the democracy of gravity, the most egalitarian of nature's forces, treating every bit of matter with perfect equality. When we think about 3i Atlas and its potential influence on planetary orbits, we must first understand this fundamental force that shapes everything in the cosmos. Gravity is not like other forces we encounter in daily life. It cannot be blocked or shielded. It extends infinitely through space, growing weaker with distance but never quite reaching zero. It operates instantaneously in Newton's framework, though Einstein showed us it actually propagates at the speed of light. rippling through the fabric of space-time itself. And perhaps most remarkably, it is always attractive, never repulsive, always pulling things together, never pushing them apart. Consider for a moment the gravitational relationship between you and 3I Atlas when it passed through our solar system. Even though the comet was millions of kilometers away, there was a real, physical force between you and it. Incredibly tiny, unmeasurably small with any instrument we possess, but real nonetheless. The comet pulled on you, and you pulled back on it with exactly the same force. Your gravitational influence, infinitesimal as it was, actually affected the trajectory of this interstellar visitor. This isn't metaphor or poetry, it's the literal truth of how gravity operates. The strength of gravity depends on just two things, mass and distance. Double the mass, and you double the force. Double the distance, and the force drops to 1/4. This simple relationship, discovered by Newton over 3 centuries ago, governs the motion of everything from falling apples to orbiting galaxies. It's a law so fundamental that we've never found a single exception to it, not in any corner of the universe we've observed. When 3I Atlas passed through our solar system, it obeyed this law perfectly, its path determined by the combined gravitational pull of the Sun and all the planets. But here's where things become wonderfully complex. In our solar system, we don't have just 2 objects pulling on each other. We have the Sun, 8 planets, dozens of moons, thousands of asteroids, millions of comets, and countless smaller pieces of debris, all pulling on each other simultaneously. This is what physicists call the N-body problem, and it's one of the most challenging problems in all of physics. When you have 3 or more bodies all gravitationally interacting, there's no simple formula that tells you where they'll all be at any future time. The only way to solve it is to calculate the forces moment by moment, step by step, watching the cosmic dance unfold through careful computation. This is precisely what scientists have been doing to understand whether 3I Atlas might have shifted planetary orbits. They've had to account for the gravitational pull of every significant body in the solar system, calculate how they all influence the comet's path, and then work out how the comet's gravity might have influenced them in return. It's a calculation of staggering complexity, requiring powerful computers and sophisticated mathematical techniques. And even then, the results come with uncertainties, ranges of possibility rather than definitive answers. The gravitational force from 3I Atlas on Earth was incredibly tiny. To put it in perspective, the gravitational pull you feel from a person standing next to you is stronger than the pull Earth felt from the comet at its closest approach. And yet, in the precise clockwork of orbital mechanics, even such tiny forces can have measurable effects over time. It's like the way a gentle breeze, barely noticeable, can eventually cause a tall building to sway if it pushes at just the right frequency. The key is not the strength of the force, but its timing and duration. When we talk about gravity as whispers, this is quite literal in a sense. Gravitational waves, predicted by Einstein and recently detected by incredibly sensitive instruments, are actual ripples in space-time that carry information about massive accelerating objects. When 3I Atlas swung around the Sun, accelerating as it changed direction, it generated gravitational waves. These waves were far too weak for us to detect directly, but they were real, spreading outward at the speed of light, carrying information about this cosmic encounter to the rest of the universe. Every acceleration of every massive object creates these gravitational waves. When you stand up, you send out gravitational waves. When Earth orbits the Sun, it creates a continuous stream of gravitational waves. When 2 black holes merge billions of light years away, they create gravitational waves strong enough that we can detect them here on Earth, even though they stretch and compress space by less than the width of a proton. The universe is filled with these overlapping ripples, these whispers of gravity carrying news of every cosmic event. The gravity of 3I Atlas didn't just affect the planets, it affected everything in the solar system. Every asteroid had its orbit shifted slightly. Every grain of dust felt the comet's pull. Even the sun itself, massive as it is, was pulled ever so slightly toward the comet. Newton's third law tells us that forces always come in pairs, equal and opposite. If the sun pulled on 3i Atlas, then 3i Atlas pulled back on the sun with exactly the same force. The difference, of course, is that the sun is so massive that this force produced an almost immeasurably small acceleration, while the same force on the much smaller comet produced a dramatic change in its trajectory. This reciprocal nature of gravity means that every gravitational interaction changes both objects involved. When the moon pulls on Earth's oceans, creating tides, Earth pulls back on the moon, gradually slowing its rotation and causing it to drift away from us at about 3.8 centimeters per year. When Jupiter pulls on asteroids, they pull back on Jupiter, causing the giant planet to wobble slightly around the solar system's center of mass. And when 3i Atlas passed through our solar system, every gravitational interaction it had changed both the comet and whatever it was interacting with. The whispers of gravity also tell stories about the internal structure of objects. As 3i Atlas approached the Sun, it experienced tidal forces, the difference in gravitational pull between its near side and far side. These tidal forces contributed to its fragmentation, literally pulling it apart. This same process happens throughout the universe. Saturn's rings exist because tidal forces prevent the material from coalescing into moons. Some comets are torn apart when they pass too close to the Sun or Jupiter. Even galaxies can be torn apart by tidal forces when they pass too close to each other. Understanding these gravitational whispers requires exquisite precision in measurement. Modern astronomy can detect changes in planetary positions of just a few meters over the course of years, even for planets billions of kilometers away. We can measure the speed of distant stars to within a few meters per second. We can detect planets around other stars by watching for the tiny wobble they induce in their parent star's motion. This precision allows us to hear gravitational whispers that would have been completely inaudible to previous generations of astronomers. The gravity of 3i Atlas also interacted with the other forces at play in the solar system. The solar wind, a stream of charged particles from the Sun, pushed on the comet's gas and dust. Radiation pressure from sunlight pushed on the dust particles. Magnetic fields influenced the charged particles in the comet's coma. All of these forces combined with gravity to determine the comet's exact path. This is why calculating the comet's gravitational influence is so complex. We have to account for all these other forces to understand exactly where the comet was and how fast it was moving at each moment. One of the most fascinating aspects of gravity is that it appears to be the weakest of nature's 4 fundamental forces, yet it dominates on cosmic scales. The electromagnetic force is about 1036 times stronger than gravity. The strong nuclear force that holds atomic nuclei together is even more powerful. Yet gravity shapes the universe because it has 2 unique properties. It has infinite range, and it's always attractive. While electrical charges can cancel out, mass always adds up. This is why gravity, despite being so weak, is the architect of cosmic structure. The weakness of gravity is actually essential for the existence of complex structures like planets, stars, and life itself. If gravity were much stronger, stars would burn out quickly, leaving no time for life to evolve. If it were much weaker, stars might not form at all, and the universe would be a cold, dark place filled with diffuse gas. The precise strength of gravity, weak as it is, seems perfectly tuned for the emergence of complexity in the universe. And this weak force is what allows objects like 3i Atlas to pass through our solar system without causing catastrophic disruptions. When we consider the gravitational influence of 3i Atlas, we must think about resonances. The planets in our solar system aren't randomly placed. They've settled into patterns where their orbital periods are related by simple ratios. For example, Neptune completes 3 orbits in almost exactly the same time Pluto completes 2. These resonances create stability. but they also mean that small perturbations can have amplified effects if they happen at just the right time. It's like pushing a child on a swing. Small pushes at the right moment can build up to large amplitudes. The fragmentation of 3I Atlas added complexity to its gravitational influence. Instead of a single mass following a single path, we had multiple fragments, each exerting its own gravitational pull. These fragments spread out along the comet's trajectory, creating an extended gravitational influence rather than a point source. It's as if the comet's gravitational whisper became a chorus, with multiple voices each contributing their own subtle influence to the cosmic conversation. The timing of gravitational interactions is crucial. If 3I Atlas had passed through our solar system when the planets were in different positions, its gravitational influence would have been completely different. A close approach to Jupiter, for instance, would have dramatically altered the comet's trajectory and might have even captured it into a bound orbit around the Sun. The specific configuration of planets during the comet's passage determined not only its path, but also its potential influence on planetary orbits. This brings us to the concept of gravitational assists or slingshots, a technique we use to accelerate spacecraft. When a spacecraft passes close to a planet, it can steal a tiny amount of the planet's orbital energy, gaining speed while the planet loses an infinitesimal amount. This same process happened with 3I Atlas. As it passed by each planet, it exchanged energy and momentum with them. The comet gained or lost speed, and the planet's orbits changed ever so slightly in response. The cumulative effect of many small gravitational perturbations can be significant over time. This is how the solar system evolved to its current configuration. Over billions of years, countless small gravitational interactions between planets, asteroids, and comets have shaped the orbits we see today. The passage of 3I Atlas is just the latest in this long history of gravitational sculpting. Its influence, however small, is now part of the solar system's gravitational history, woven into the complex tapestry of forces that determine planetary motions. Gravity also operates on scales much larger than our solar system. Our Sun and all its planets are falling toward the center of the Milky Way galaxy, held in orbit by the combined gravity of hundreds of billions of stars. The galaxy itself is falling toward the Andromeda Galaxy, with which will collide in about 4.5 billion years. And both galaxies are part of the Local Group, which is falling toward the Virgo cluster, which is itself part of larger structures all shaped by gravity's invisible hand. When 3I Atlas entered our solar system, it brought with it a tiny piece of the galaxy's gravitational field. Its trajectory was shaped not just by its last stellar encounter, but by the combined gravitational influence of all the stars it had passed near during its interstellar journey. In a sense, it carried gravitational memories of its travels, encoded in its velocity and direction of approach. By studying its trajectory, we can learn something about the gravitational environment of our local region of the galaxy. The precision with which we can now measure gravitational effect is truly remarkable. The LIGO and Virgo gravitational wave detectors can measure changes in distance smaller than 1,000th of the width of a proton. The Gaia Space Telescope is measuring the positions and velocities of over 1 billion stars with unprecedented precision, allowing us to map the gravitational field of our galaxy in extraordinary detail. These technological achievements allow us to hear gravitational whispers from across the universe. As 3I Atlas recedes into the distance, its gravitational influence on our solar system doesn't suddenly stop. Gravity has infinite range, so the comet continues to pull on Earth, and all the other planets even now, though the force grows weaker with each passing moment. By the time you wake up tomorrow, the gravitational force between Earth and 3I Atlas will have decreased by a measurable amount, but it will never reach exactly zero. We are forever gravitationally connected to this interstellar visitor, bound by invisible threads that stretch across the cosmos. This permanent connection is true for every gravitational interaction. Every object that has ever passed through our solar system has left its gravitational signature on planetary orbits. Every meteor that has struck Earth, every comet that has graced our skies, every asteroid that has passed nearby, all of them have contributed to Earth's current orbit. We are where we are, literally, because of the cumulative effect of countless gravitational interactions over billions of years. The study of these gravitational whispers is revealing surprises about our solar system. For instance, careful analysis of planetary orbits suggests that our solar system might have had additional planets in the past that were ejected through gravitational interactions. The current orbits of the planets preserve faint memories of these lost worlds, gravitational echoes of siblings that were cast out into interstellar space billions of years ago. Perhaps one day, one of these ejected planets will pass through another star system as an interstellar visitor, just as 3I Atlas passed through ours. Gravity also whispers to us about invisible things. The motion of stars tells us about dark matter, invisible material that makes up most of the mass in galaxies. The acceleration of the universe's expansion tells us about dark energy, a mysterious force that opposes gravity on cosmic scales. The orbits of stars near the center of our galaxy reveal a supermassive black hole, invisible but unmistakable in its gravitational influence. We live in a universe where most of the gravitational sources are invisible, detectable only through their whispers. The gravitational influence of 3I Atlas might seem insignificant compared to these cosmic forces, but it's part of the same phenomenon. Every bit of gravity, no matter how small, contributes to the whole. The universe is a vast gravitational network with every object connected to every other object through these invisible forces. The passage of an interstellar comet through our solar system is just one thread in this cosmic web, but it's a thread that connects us to the wider galaxy in a tangible physical way. As we listen to these gravitational whispers, we're also learning to speak the language of gravity ourselves. We use gravitational assists to send spacecraft to the outer planets. We're developing technologies to detect gravitational waves from cosmic events. Some scientists even propose using artificial gravitational waves to communicate across interstellar distances. We're becoming active participants in the gravitational conversation of the cosmos, no longer just passive listeners. The possibility that 3I Atlas shifted planetary orbits, even slightly, is a reminder of the dynamic nature of our cosmic environment. We tend to think of the solar system as fixed and unchanging, but it's actually a dynamic system constantly responding to gravitational influences both internal and external. The planets migrate slowly over millions of years. The moon drifts away from Earth. The sun itself oscillates slightly as it orbits the galactic center. Everything is in motion. Everything is changing, all choreographed by gravity's invisible hand. This cosmic dance has been going on for billions of years and will continue for billions more. Long after our sun has died, long after Earth itself is gone, the gravitational influences set in motion by 3I Atlas and countless other objects will continue to propagate through space. The whispers of gravity are eternal, carrying information about every mass and every motion forward through time. In this way, every gravitational interaction is immortal, its influence spreading outward through the universe forever. As you lie there in the quiet darkness, you can almost feel these gravitational whispers surrounding you. The gentle pull of the moon, raising tides in Earth's oceans and in your own body, which is mostly water. The steady pull of the sun, holding Earth in its life-giving orbit. The subtle pulls of the planets, each adding their voice to the gravitational chorus. And somewhere out there, growing fainter but never quite silent, the whisper of 3I Atlas continues its journey through space, carrying with it the gravitational memory of its encounter with our solar system. These whispers tell us we're not alone, not isolated, but part of a vast gravitational community that extends throughout the universe. Every star, every planet, every comet and asteroid, every grain of dust floating in space, all are connected through these invisible threads of gravity. We're all part of the same cosmic dance, all responding to the same fundamental force, all whispering to each other across the vast distances of space. And occasionally, when an interstellar visitor like 3 Atlas passes through, those whispers become a little louder, reminding us of our connection to the cosmos beyond our own small corner of space. The delicate balance of orbits that keeps our solar system stable is one of nature's most remarkable achievements. Picture, if you will, the planets as dancers in an elaborate ballet that has been choreographed over billions of years. Each dancer knows their role perfectly, following paths that have been refined by countless rehearsals, each movement precisely timed to maintain the harmony of the whole. This is not a rigid, mechanical dance, but a fluid, dynamic performance, where each participant responds to all the others, adjusting their movements in response to the subtle cues of gravity. Earth's orbit, which seems so steady and reliable to us, is actually the result of a complex equilibrium between competing forces. We're falling toward the sun, pulled by its massive gravity, but we're also moving sideways fast enough that we keep missing it. This balance between inward pull and sideways motion creates our nearly circular path around the sun. But it's not a perfect circle. Earth's orbit is slightly elliptical, bringing us about 5 million kilometers closer to the sun in January than in July. This ellipticity itself changes over time, becoming more circular or more elongated in cycles that last tens of thousands of years. The other planets experience similar orbital variations, and these variations are not independent. They're coupled together through gravitational interactions, creating a complex web of influences. Jupiter, with its enormous mass, acts like a gravitational anchor for the solar system, its influence felt by every other planet. Saturn, Uranus, and Neptune add their own gravitational voices to the chorus. Even tiny Mercury, racing around the sun every 88 days, contributes its small part to the gravitational symphony that determines everyone's orbit. This interconnected system of orbits has evolved over billions of years to reach its current configuration. In the early solar system, the planets probably formed in different locations from where we see them today. Through a process called planetary migration, driven by gravitational interactions with a disk of gas and dust from which they formed and with each other, the planets slowly moved to their current positions. Jupiter probably migrated inward and then back outward. Neptune and Uranus might have switched places. This cosmic reshuffling continued until the system settled into a stable configuration, the delicate balance we observe today. But this balance is not static. It's what physicists call a dynamic equilibrium, constantly adjusting to small perturbations. Every asteroid that passes by, every comet that falls toward the sun, every piece of interplanetary dust that spirals inward, slightly disturbs this balance. The planets respond to these perturbations like a master tightrope walker adjusting to a gust of wind, making tiny corrections to maintain stability. Most of the time, these adjustments are so small that they're imperceptible even to our most sensitive instruments. The passage of 3i Atlas through this delicately balanced system was like a pebble dropped into a still pond. The ripples it created were tiny, but they spread throughout the entire system. Each planet felt the comet's gravitational pull differently, depending on their mass and their distance from the comet's path. Earth, being relatively small and not particularly close to the comet's trajectory, would have experienced only the tiniest perturbation. Jupiter, with its enormous mass, would have felt a stronger pull but would have been less affected due to its much greater inertia. To understand how these perturbations might affect planetary orbits, we need to consider the concept of orbital elements. An orbit is completely described by 6 numbers: the size of the ellipse, its shape, its orientation in space, and the position of the planet along the orbit at a specific time. A gravitational perturbation from a passing object like 3i Atlas can change any or all of these elements. The orbit might become slightly larger or smaller, more circular or more elliptical, tilted differently relative to the solar system's plane, or rotated to point in a different direction. These changes accumulate over time through a process called orbital evolution. A tiny change in Earth's orbital speed, perhaps just a few millimeters per second might seem negligible. But as Earth continues its orbit, this small change causes it to be in a slightly different position than it would have been otherwise. Over years, decades, centuries, and millennia, these positional differences grow. It's like two hikers starting from the same point, but walking in directions that differ by just 1 degree. At first, they're side by side, but after walking for miles, they're far apart. The stability of planetary orbits depends on what mathematicians call phase space, an abstract realm where each point represents a possible state of the system. Some regions of phase space correspond to stable orbits that can persist for billions of years. Other regions are chaotic, where small changes lead to dramatically different outcomes. Our solar system's current configuration sits in a stable region of phase space, which is why the planets have maintained their regular orbits for so long. But we're not infinitely far from the chaotic regions. Given enough perturbations over enough time, planetary orbits could potentially become unstable. This is where the influence of objects like 3i Atlas becomes philosophically interesting. Each perturbation, no matter how small, moves the solar system to a slightly different point in phase space. Most of the time, we remain well within the stable region. But over billions of years, with countless small perturbations accumulating, the system slowly explores different parts of phase space. It's a random walk through the space of all possible orbital configurations, guided by the accumulated effects of every gravitational interaction. The mathematical framework for understanding these orbital perturbations was developed by brilliant minds like Joseph-Louis Lagrange, Pierre-Simon Laplace, and Henri Poincaré. They discovered that planetary orbits could be described as a main elliptical motion, plus an infinite series of small corrections. Each correction accounts for the gravitational influence of other planets, and these corrections have their own corrections, creating a hierarchy of ever smaller effects. Calculating these to high precision requires powerful computers and sophisticated numerical methods. When scientists model the potential orbital changes from 3i Atlas, they use techniques like symplectic integration, which preserves the fundamental mathematical properties of orbital motion even over billions of simulated years. They run thousands of simulations with slightly different initial conditions, exploring the range of possible outcomes. Some simulations show essentially no change to planetary orbits. Others show small but measurable shifts. The range of outcomes reflects our uncertainty about the comet's exact mass, trajectory, and fragmentation history. The concept of orbital resonance adds another layer of complexity to this picture. When two planets have orbital periods that form a simple ratio, like 2.1 or 3:2, they're in resonance. These resonances can either stabilize or destabilize orbits, depending on their exact nature. Our solar system has several important resonances. Neptune and Pluto are in a 3.2 resonance, which keeps Pluto from ever coming too close to Neptune despite their orbits crossing. Jupiter and Saturn are near a 5.2 resonance, which has profound effects on the asteroid belt. If a perturbation from 3i Atlas shifted a planet's orbit even slightly, it could affect these resonances. A planet might be pushed closer to or farther from a resonance, changing how it interacts with other planets. Over millions of years, these changed interactions could lead to significant orbital evolution. It's like adjusting the tuning of one string on a guitar. All the harmonic relationships change, creating a different overall sound. The stability of Earth's orbit is particularly important because it directly affects our climate and the habitability of our planet. Earth's orbital eccentricity varies between nearly circular and slightly elliptical over a period of about 100,000 years. The tilt of Earth's axis wobbles between 22.1 and 24.5 degrees over 41,000 years. The direction Earth's axis points processes like a spinning top over 26,000 years. These cycles, known as Milankovitch cycles, drive long-term climate changes, including ice ages. If 3i Atlas caused even a tiny change to Earth's orbit, it could affect the timing and intensity of future ice ages. A slightly more elliptical orbit might make summers hotter and winters colder. a change in axial tilt might shift climate zones. These effects would unfold over thousands and millions of years, far too slowly for any single generation to notice, but potentially significant for the long-term evolution of life on Earth. The delicate balance of planetary orbits has allowed Earth to maintain liquid water on its surface for billions of years, a remarkable achievement given the many things that could have gone wrong. Venus, just slightly closer to the Sun, experienced a runaway greenhouse effect that turned it into a hellish world, with surface temperatures hot enough to melt lead. Mars, slightly farther from the Sun and much smaller, lost most of its atmosphere and water, becoming a cold, dry desert. Earth sits in the sweet spot, the habitable zone, where conditions are just right for life as we know it. This habitable zone itself depends on orbital stability. If Earth's orbit became significantly more elliptical, we might freeze when far from the Sun and bake when close to it. If our orbit decayed, bringing us closer to the Sun, we might suffer Venus's fate. If we drifted outward, we might become like Mars. The fact that Earth has remained in the habitable zone for billions of years, despite countless gravitational perturbations from passing asteroids, comets, and even interstellar visitors, is testament to the remarkable stability of our orbital configuration. But this stability shouldn't be taken for granted. Computer simulations of the solar system's future evolution show that while the orbits are stable for millions of years, there's a small but non-zero chance of instability over billions of years. Mercury's orbit is particularly vulnerable, with about a 1% chance of becoming unstable before the Sun dies. If Mercury's orbit became highly elliptical, it could potentially collide with Venus or even Earth, or be ejected from the solar system entirely. Such an event would destabilize the entire inner solar system. The influence of interstellar visitors like 3I Atlas on these long-term stability calculations is still being studied. Each visitor adds a random element to the solar system's evolution, a roll of the cosmic dice that could either increase or decrease stability depending on the specific circumstances of the encounter. Over billions of years, with potentially thousands of interstellar objects passing through, these random influences could accumulate into significant effects. The outer planets, particularly Jupiter, play a crucial role in maintaining the stability of the inner solar system. Jupiter's massive gravity acts like a shield, deflecting many comets and asteroids that might otherwise impact Earth. But Jupiter can also destabilize orbits, sending asteroids from the asteroid belt into the inner solar system. This dual role, protector and threat, exemplifies the complex nature of gravitational interactions in multi-body systems. The asteroid belt itself exists in a delicate gravitational balance between the Sun and Jupiter. The asteroids occupy specific regions where orbits are stable, avoiding resonances with Jupiter that would quickly eject them. The gaps in the asteroid belt, known as Kirkwood gaps, correspond to orbital resonances with Jupiter, where asteroids cannot maintain stable orbits. If a passing interstellar object like 3I Atlas perturbed asteroids near these boundaries, it could send them into unstable orbits, potentially creating new Earth-crossing asteroids. Saturn's rings provide a beautiful example of orbital dynamics on a smaller scale. The rings consist of billions of particles, from tiny dust grains to house-sized boulders, all orbiting Saturn in a thin disk. The rings have gaps and divisions caused by gravitational resonances with Saturn's moons. Tiny shepherd moons orbit within the rings, their gravity keeping ring particles in narrow bands. This system is incredibly sensitive to perturbations. Even a small change can create waves and distortions that propagate through the rings. If we could somehow shrink 3I Atlas down and send it through Saturn's rings, we would see dramatic effects. Waves spreading outward from its passage, particles scattered from their orbits, temporary gaps opening and closing. The same physics applies to the solar system as a whole, just on a much larger scale and over much longer timescales. The passage of 3I Atlas through our solar system created gravitational waves in the orbital fabric of the planets, too subtle for us to see directly, but potentially significant over cosmic time. The search for Planet 9, a hypothetical large planet in the outer solar system, illustrates how sensitive orbital dynamics can be to gravitational perturbations. The orbits of several distant Kuiper Belt objects seem to be clustered in a way that suggests they're being shepherded by a massive, undiscovered planet. If Planet 9 exists, it would have profound effects on the stability of the outer solar system, and if 3I Atlas passed anywhere near Planet 9's hypothetical orbit, the gravitational interaction could have been much stronger than its interactions with the known planets. The study of exoplanetary systems has revealed just how special our solar system's orbital configuration might be. Many exoplanetary systems have hot Jupiters, massive planets orbiting very close to their stars. Others have planets in highly elliptical orbits or orbits that are strongly inclined to each other. Some systems are so tightly packed that adding another planet anywhere would destabilize the whole system. Our solar system, with its well-spaced, nearly circular coplanar orbits, might be relatively rare. This raises profound questions about the role of chance in planetary system evolution. If interstellar visitors like 3I Atlas are common, and if they can perturb planetary orbits even slightly, then the current configuration of any planetary system depends partly on the random history of such encounters. A system that experienced many close encounters might have chaotic, unstable orbits. A system that experienced few encounters might retain its primordial configuration. Our solar system, with its stable but not boringly regular orbits, might represent a middle ground. The fragmentation of 3I Atlas adds another dimension to its potential orbital influence. As the comet broke apart, conservation of momentum meant that the fragments pushed off each other, sending them on slightly different trajectories. Each fragment then exerted its own gravitational influence on the planets. This distributed perturbation might have actually reduced the overall effect on any single planet, spreading the gravitational influence over a larger region of space and time. As we contemplate these orbital mechanics, it's worth remembering that we're not passive observers, but active participants. Every spacecraft we launch changes Earth's orbit by an infinitesimal amount. When we send probes to other planets, we're adding our own perturbations to the cosmic dance. The Voyager spacecraft, now in interstellar space, will eventually pass through other star systems, potentially perturbing their planets, just as 3I Atlas might have perturbed ours. The delicate balance of planetary orbits is also affected by non-gravitational forces. The Sun is slowly losing mass as it converts hydrogen to helium and radiates energy. This mass loss causes all planetary orbits to slowly expand. Solar radiation pressure pushes on planets, though this effect is tiny for massive bodies like Earth. The Yarkovsky effect, caused by the uneven heating and cooling of rotating bodies, can significantly alter the orbits of small asteroids over millions of years. All of these effects combine with gravitational perturbations to shape the long-term evolution of orbits. Tidal forces add yet another layer of complexity. The Moon raises tides on Earth, and Earth raises even larger tides on the Moon. These tidal interactions transfer angular momentum from Earth's rotation to the Moon's orbit, causing the Moon to slowly spiral outward, while Earth's rotation slows. Similar tidal interactions occur throughout the solar system. If 3I Atlas passed close enough to any planet to create significant tidal forces, it could have affected not just the planet's orbit but also its rotation rate and the orbits of its moons. The concept of the invariable plane illustrates the deep stability of our solar system. This plane, perpendicular to the total angular momentum vector of the solar system, has remained essentially fixed for billions of years. Individual planetary orbits precess and wobble, but they do so around this invariable plane. It's like a cosmic gyroscope maintaining its orientation despite all the perturbations and interactions. The passage of 3I Atlas might have caused tiny wobbles, but it couldn't significantly change this fundamental orientation. As we look to the future, the delicate balance of planetary orbits faces new challenges. In about 1 billion years, the Sun will be significantly brighter than it is today, pushing the habitable zone outward. Earth might become too hot for life unless we can somehow adjust its orbit. In 5 billion years, the Sun will begin its death throes, expanding into a red giant that might engulf the inner planets. The orbital dynamics of the solar system will become increasingly chaotic as the Sun loses mass and planets respond to the changing gravitational field. But for now, for the next millions of years at least, the delicate balance holds. The planets continue their ancient dance, following paths refined by billions of years of gravitational interactions. Each orbit is a masterpiece of cosmic engineering, a solution to the complex equations of motion that has proven stable against countless perturbations. The passage of 3I Atlas was just the latest test of this stability, a cosmic stress test that our solar system passed with flying colours. As you drift there in the darkness, you're riding on one of these perfectly balanced orbits. Earth carries you around the Sun at about 30 kilometers per second, a speed that would take you around Earth's equator in just over 20 minutes. Yet this tremendous motion feels perfectly smooth, perfectly stable, because the balance is so precise. You're part of a cosmic ballet that has been performing for billions of years, a dance so well rehearsed that even the unexpected appearance of an interstellar visitor can't disrupt its rhythm. The possibility that 3I Atlas might have shifted this balance, even by the tiniest amount, connects us to the dynamic nature of the cosmos. We're not living in a static, unchanging universe, but in one where everything is in constant motion, constant evolution. The orbits we see today are not the orbits that existed a billion years ago, nor are they the orbits that will exist a billion years from now. They're snapshots of an ongoing process, frames in a cosmic movie that has been playing since the birth of the solar system and will continue until its end. This perspective transforms our understanding of planetary motion from a mechanical process to an organic evolution. The solar system is not a clock, ticking away with mechanical precision, but a living system that responds and adapts to influences both internal and external. Each planet's orbit is a story written by gravity over billions of years, a story to which 3I Atlas has now added its own small chapter. And as we study these orbits with ever greater precision, we're learning to read these gravitational stories, to understand the history and future of our cosmic neighborhood. The hypothesis of a gentle nudge from 3I Atlas opens a window into one of the most profound questions in astronomy. How sensitive is our cosmic environment to small changes? Imagine, if you will, that we could rewind the history of the solar system and play it again, but this time with 3I Atlas arriving just a few years earlier or later, or approaching from a slightly different angle, or having a slightly different mass. Would the solar system evolve exactly the same way? Would Earth still be in exactly the same orbit? Would we still be here to ask these questions? This is not merely an academic exercise, but touches on fundamental questions about determinism and chaos in physical systems. The solar system, with its multiple gravitationally interacting bodies, exhibits what scientists call sensitive dependence on initial conditions. This means that tiny differences in starting conditions can lead to dramatically different outcomes over long periods of time. It's the cosmic equivalent of the butterfly effect, where a butterfly flapping its wings in Brazil might theoretically trigger a tornado in Texas weeks later. In our case, the butterfly is 3I Atlas, and the tornado might be a shifted planetary orbit millions of years in the future. Let's explore this hypothesis gently, without alarm, recognizing that we're talking about changes so small they wouldn't affect life on Earth for millions of years, if ever. When 3I Atlas passed through our solar system, it came within about 150 million kilometers of Earth. At this distance, its gravitational pull on our planet was extraordinarily weak, perhaps a billionth of the Sun's pull. To put this in perspective, the gravitational effect of 3I Atlas on Earth was less than the effect of a commercial airliner flying overhead has on you. And yet, in the precise mathematics of orbital mechanics, even such tiny forces can accumulate over time. The key to understanding how such a small force might matter lies in the concept of orbital phase. Earth's position in its orbit at any given moment determines where it will be at all future moments, assuming no perturbations. If 3i Atlas changed Earth's velocity by even a tiny amount, say a millimeter per second, this would cause Earth to be in a slightly different position as it continues its orbit. After 1 year, Earth might be a few kilometers from where it would have been otherwise. After 1,000 years, the difference might be thousands of kilometers. After 1,000,000 years, Earth might be on the opposite side of its orbit from where it would have been without the perturbation. This accumulation of positional differences doesn't mean Earth's orbit becomes wildly different. Instead, it means that Earth's phase, its position along its orbit at any given time, slowly drifts relative to what it would have been. This is like two clocks that run at almost exactly the same rate, but differ by a tiny amount. At first, they show nearly the same time, but over years and decades, they drift apart until they show completely different times. The clocks are still keeping time accurately. They're just out of phase with each other. Now, consider what this means for Earth's interactions with other planets. The gravitational forces between planets depend on their relative positions. When Earth and Jupiter are on the same side of the Sun, Jupiter's pull on Earth is different than when they're on opposite sides. If 3i Atlas shifted Earth's orbital phase, it would change the timing of these planetary interactions. Over millions of years, these changed interactions could lead to different orbital evolution than would have occurred otherwise. The hypothesis becomes even more intriguing when we consider that 3i Atlas fragmented into multiple pieces. Each fragment followed a slightly different path through the solar system, creating what we might call a gravitational shower rather than a single perturbation. Some fragments might have passed closer to certain planets than others. The combined effect of all these fragments would have created a complex pattern of perturbations, different for each planet. It's as if the solar system received not one gentle nudge, but a series of tiny taps, each one adding its own subtle influence to the orbital dynamics. Computer simulations of this scenario reveal fascinating possibilities. In some simulations, the perturbations from 3i Atlas cause no significant changes to planetary orbits even over billions of years. The solar system's inherent stability absorbs the perturbation, like a well-designed building absorbing the force of wind. In other simulations, however, the perturbations trigger a cascade of changes. Earth's orbit might become slightly more elliptical, Mars might drift slowly outward, the asteroid belt might become more dynamically active. None of these changes would be dramatic or dangerous, but they would represent a different evolutionary path for our solar system. The timing of the encounter matters enormously. If 3i Atlas had arrived when Earth was at a different point in its orbit, or when Jupiter and Saturn were in different relative positions, the gravitational interactions would have been completely different. This is where the element of cosmic chance enters our story. Specific configuration of the solar system at the moment of 3i Atlas's passage was the result of billions of years of orbital evolution. A different timing by even a few months would have meant different gravitational interactions and different potential consequences. This brings us to a profound realization. The current state of our solar system is partly the result of random encounters with objects like 3i Atlas throughout its history. If we could somehow catalogue every asteroid, every comet, every interstellar visitor that has passed through our solar system over the past 4.6 billion years, we would find that each one contributed its own tiny perturbation to planetary orbits. The cumulative effect of all these perturbations has shaped the solar system we see today. Some scientists have proposed that these random perturbations might actually be essential for the long-term stability of planetary systems. It's counterintuitive, but adding a small amount of random noise to a dynamic system can sometimes prevent it from falling into unstable resonances. It's like adding a small vibration to prevent a bridge from resonating at its natural frequency during high winds. The passages of objects like 3 Atlas might provide just enough randomness to keep planetary orbits from becoming locked into potentially dangerous configurations. The hypothesis of a gentle nudge also connects to larger questions about the formation and evolution of planetary systems throughout the galaxy. If interstellar objects regularly pass through star systems and perturb planetary orbits, then every planetary system's configuration is partly determined by its history of such encounters. Systems in denser regions of the galaxy, where stars are closer together and interstellar objects more common, might have more chaotic planetary orbits. Systems in sparse regions might retain more primordial, regular orbits. Our solar system appears to be in a relatively quiet region of the galaxy, the local bubble, where the density of interstellar material is lower than average. This might have protected us from frequent encounters with massive interstellar objects, allowing our planetary orbits to remain relatively stable. But we haven't always been in this quiet region. As the Sun orbits the galactic center, it passes through regions of varying density. During passages through spiral arms or molecular clouds, the rate of interstellar encounters would increase, potentially leading to periods of enhanced orbital perturbation. The fragmentation of Thruai or Atlas provides a natural experiment in how comet breakups might affect planetary orbits. When a comet fragments, the pieces don't just drift apart randomly. They're ejected with specific velocities determined by the forces that cause the fragmentation. Some pieces might be thrown forward along the comet's trajectory, arriving at planetary encounters earlier than the main body would have. Others might be thrown backward, arriving later. This temporal spreading of the gravitational influence might actually reduce the overall perturbation on any single planet, distributing the effect over time. But fragmentation can also create resonant effects. If the fragments pass by a planet at intervals that match some natural frequency of the planet's orbit, the perturbations could add constructively, amplifying the overall effect. It's like pushing a swing at just the right moment to build up amplitude. The specific pattern of Thruai Atlas's fragmentation, the sizes and velocities of the pieces, might have created such resonant interactions with one or more planets. The hypothesis extends beyond just orbital changes to potential effects on planetary geology and climate. If Thruai Atlas shifted Earth's orbit even slightly, it could affect the timing and intensity of ice ages. Earth's climate is sensitive to orbital parameters through the Milankovitch cycles. A small change in orbital eccentricity or axial tilt could shift the phase of these cycles, potentially advancing or delaying the next ice age by thousands of years. While this wouldn't affect us or even our distant descendants, it could have profound implications for the evolution of life on Earth over geological timescales. Consider also the potential effects on the asteroid belt. The asteroids exist in a complex web of gravitational relationships with the planets, particularly Jupiter. If Thruai Atlas perturbed any asteroids even slightly, it could have shifted them into different orbital families or even onto planet-crossing orbits. Over millions of years, these shifted asteroids might collide with planets or be ejected from the solar system, changing the impact history of the inner planets. A single asteroid shifted onto an Earth-crossing orbit could, millions of years from now, create a crater like the one that ended the age of dinosaurs. The hypothesis of a gentle nudge from Thruai Atlas also raises questions about detection and measurement. How would we know if planetary orbits had been shifted? The changes would be so small that they might be lost in the noise of our measurements. We've only been tracking planetary positions with high precision for a few decades, a tiny fraction of an orbital period for the outer planets. Detecting a change of a few meters in Earth's orbit, or a few kilometers in Jupiter's orbit, pushes the limits of our current technology. Future missions and observations might provide answers. The European Space Agency's Gaia mission is measuring stellar positions with unprecedented precision, which will improve our knowledge of the solar system's motion through the galaxy. NASA's proposed Near-Earth Object Surveyor mission will detect many more asteroids and comets, potentially including future interstellar visitors. As our baseline of observations extends over decades and centuries, we'll be able to detect ever smaller orbital changes, perhaps eventually confirming whether Thruai Atlas really did nudge our planets. The philosophical implications of this hypothesis are profound. If a small comet from another star system can alter planetary orbits, then the configuration of our solar system is not purely deterministic, but contains an element of cosmic chance. The exact position of Earth in its orbit right now depends partly on random encounters with interstellar objects throughout history. This adds a layer of contingency to our existence. If Earth's orbit were slightly different, would complex life have evolved? Would humanity have emerged? Are we here partly because of the specific history of gentle nudges our planet has received? This connects to the anthropic principle, the observation that the universe seems fine-tuned for the existence of observers like us. Perhaps part of this fine-tuning isn't in the fundamental laws of physics, but in the specific history of random events that shaped our solar system. The passages of interstellar objects like 3i Atlas might be part of a cosmic lottery that occasionally produces planetary systems suitable for life. Most systems might be perturbed into configurations hostile to life, but a few, including ours, might receive just the right series of gentle nudges to create and maintain habitable conditions. As we contemplate this hypothesis, it's important to maintain perspective. Even if 3i Atlas did shift planetary orbits, the changes are tiny compared to the normal variations that occur over geological time. Earth's orbit naturally varies in eccentricity, inclination, and other parameters due to gravitational interactions with other planets. These natural variations are well understood and have been occurring throughout Earth's history without preventing the development and flourishing of life. Any additional variation from 3i Atlas would be a small addition to these natural cycles. The hypothesis of a gentle nudge also highlights the interconnectedness of cosmic phenomena. An object that formed around a distant star billions of years ago travelled across the galaxy and briefly interacted with our solar system, potentially altering our future in subtle ways. We are not isolated. We're part of a galactic community where star systems occasionally exchange material and gravitational influences. Every star we see in the night sky has probably experienced similar visitations, and some of the comets in our own Oort cloud might one day visit other star systems, carrying with them the gravitational influence of our Sun. As technology advances, we might one day be able to track the origins and destinations of interstellar visitors with greater precision. By combining observations of objects like 3i Atlas with models of stellar motion in our galaxy, we might be able to trace them back to their parent stars or forward to future stellar encounters. This would allow us to map the network of gravitational influences connecting star systems, revealing the hidden threads that bind the galaxy together. The gentle nudge hypothesis also has implications for the search for extraterrestrial life. If planetary orbits can be shifted by interstellar visitors, then the habitable zones around stars might be more dynamic than we thought. A planet that's currently too cold for liquid water might be nudged into a warmer orbit. A planet that's currently habitable might drift into an orbit too hot or too cold for life. This adds another variable to the Drake equation, another factor determining how many civilizations might exist in our galaxy. Looking forward, the hypothesis suggests that our solar system's future evolution might depend partly on chance encounters with future interstellar visitors. We can predict planetary positions accurately for millions of years assuming no external perturbations, but we can't predict when the next 3i Atlas will arrive, or how it might affect our orbits. This fundamental unpredictability adds an element of cosmic suspense to our future. The solar system's fate isn't entirely predetermined but will be shaped by random encounters we can't foresee. Yet this unpredictability shouldn't cause anxiety. The solar system has survived billions of years of such encounters and remains remarkably stable. The chances of a catastrophic perturbation from an interstellar visitor are extraordinarily small. Instead, these gentle nudges add richness and complexity to the solar system's evolution, ensuring that its future will be as interesting and dynamic as its past. Each visitor writes a new chapter in the ongoing story of our cosmic neighborhood, a story in which stability and change, order and chaos, predictability and surprise are all woven together in the grand tapestry of orbital evolution. the search for echoes in time begins with a simple question. If 3 Atlas really did nudge our planets, even infinitesimally, how would we ever know? It's like trying to hear a whisper in a concert hall after the orchestra has stopped playing, searching for the faintest reverberation of a sound that has already faded into silence. Yet this is precisely what modern astronomy attempts to do, using instruments of extraordinary sensitivity and techniques of remarkable sophistication to detect the subtle signatures of past cosmic events encoded in the present motions of celestial bodies. Scientists have become cosmic archaeologists, digging through layers of gravitational history preserved in planetary orbits. Every planet's current position and velocity contains information about every gravitational interaction it has ever experienced. It's as if each planet carries within its motion a complete autobiography, written in the language of orbital mechanics, chronicling every significant encounter throughout its billions of years of existence. The challenge lies in learning to read this autobiography, to extract from the present configuration of the solar system information about events that happened in the distant past. The tools we use for this cosmic archaeology are both terrestrial and space-based. On Earth, radio telescopes track the positions of planets by bouncing radar signals off their surfaces and measuring the return time with extraordinary precision. We can determine the distance to Mars, for instance, to within a few centimeters, even though it's hundreds of millions of kilometers away. Optical telescopes measure planetary positions against the background stars, building up decades-long records of orbital motion. These measurements are so precise that we can detect the slight wobble in a planet's motion caused by the gravitational pull of its moons. In space, missions like the Gaia Observatory are revolutionizing our ability to measure positions and motions. Gaia is measuring the positions of over 1 billion stars with micro-arc-second precision, equivalent to measuring the width of a human hair from 1,000 kilometers away. While Gaia primarily observes stars, it also tracks asteroids and, when possible, interstellar objects like 3I Atlas. This unprecedented precision allows us to build a 3-dimensional map of our galaxy's gravitational field and understand how objects move through it. The search for echoes of 3 Atlas's passage requires us to understand what we're looking for. A gravitational perturbation doesn't just change a planet's position, it can affect various orbital parameters in subtle ways. The semi-major axis, which determines the size of the orbit, might increase or decrease slightly. The eccentricity, which measures how elliptical the orbit is, might change. The inclination, the tilt of the orbit relative to the solar system's plane, might shift. The longitude of perihelion, which determines the orientation of the ellipse in space, might rotate. Each of these parameters evolves naturally over time due to planetary interactions, but an encounter with 3I Atlas would add an additional component to this evolution. To detect these changes, scientists use a technique called orbital determination. By observing a planet's position at many different times, they can calculate the orbital parameters that best fit all the observations. The more observations they have, and the longer the time span they cover, the more precisely they can determine the orbit. Modern orbital determinations for the planets are so precise that they can predict positions centuries into the future with errors of only a few kilometers. Any deviation from these predictions might indicate an unaccounted-for perturbation, possibly from an interstellar visitor. The challenge is that the expected perturbations from 3I Atlas are extremely small, possibly smaller than the current uncertainties in our orbital determinations. It's like trying to measure the growth of a tree by observing it for just a few seconds. The change is real, but too slow to detect directly. We need either much longer observation baselines or much more precise measurements, or ideally both. This is why the search for echoes of 3I Atlas is a long-term project that might take decades or even centuries to yield definitive results. One promising approach is to look for correlations in orbital changes across multiple planets. If 3I Atlas perturbed the solar system, it would have affected all the planets, though to different degrees depending on their masses and distances from the comet's path. By looking for a pattern of orbital changes consistent with a single perturbing object passing through the solar system at a specific time, scientists might be able to identify the signature of 3I Atlas, even if the individual perturbations are too small to detect with certainty. Computer simulations play a crucial role in this search. Scientists create detailed models of the solar system, including all known gravitational influences, and then add 3I Atlas with various assumed masses and trajectories. They run these simulations forward in time to see what orbital changes would result, and then compare these predictions with observations. If a particular model of 3I Atlas produces orbital changes that match what we observe, it provides evidence that the comet really did perturb the planets. But with so many unknowns about the comet's exact properties, many different models must be tested. The fragmentation of 3I Atlas complicates this modeling significantly. Instead of a single mass following a single trajectory, we have multiple fragments, each with its own mass and path. The gravitational effect of the original comet has been distributed among these fragments in a way that's difficult to reconstruct. Some fragments were too small to detect from Earth, but they still contributed to the total gravitational influence. It's like trying to reconstruct a shattered vase when you only have some of the pieces. You can guess at the overall shape, but the details remain uncertain. Another approach to finding echoes of 3I Atlas is to study the asteroid belt. Asteroids are much less massive than planets, making them more susceptible to gravitational perturbations. If 3I Atlas passed through or near the asteroid belt, it might have noticeably altered the orbits of some asteroids. By looking for asteroids with orbital changes that can't be explained by known influences, scientists might find evidence of the comet's passage. This is particularly promising for asteroids that were near orbital resonances, where small perturbations can have amplified effects. The Kuiper belt and the Oort cloud offer additional opportunities to search for echoes. These distant regions contain countless small bodies whose orbits preserve a record of gravitational influences over billions of years. If 3I Atlas passed through these regions on its way into or out of the solar system, it might have scattered some objects onto new trajectories. Some of these scattered objects might eventually become visible as long-period comets falling toward the Sun. By studying the orbits of such comets, we might be able to trace them back to an encounter with 3I Atlas. The search for echoes also extends to the planet's moons. Each moon system is like a miniature solar system, with the moons orbiting their planet much as the planets orbit the Sun. If 3I Atlas passed close enough to a planet to significantly perturb it, it would also have affected the orbits of that planet's moons. These changes might be easier to detect than changes to the planet's orbit around the Sun because the moon's orbital periods are much shorter, allowing changes to accumulate more quickly. For Earth's moon, we have extraordinarily precise measurements thanks to the laser retroreflectors placed on the lunar surface by the Apollo missions. By bouncing laser beams off these reflectors, scientists can measure the Earth-Moon distance to within millimeters. This precision has allowed us to detect tiny changes in the Moon's orbit due to tidal interactions, general relativity, and other effects. If 3I Atlas caused even a tiny change in the Moon's orbit, these laser-ranging measurements might eventually detect it. The search for gravitational echoes has led to the development of new mathematical techniques. Chaos theory, originally developed to understand weather patterns, is now applied to planetary orbits. Scientists use tools like Lyapunov exponents to measure how quickly nearby orbits diverge, indicating the degree of chaos in the system. They use frequency analysis to identify the fundamental periods and resonances in planetary motion. They use symplectic integrators to ensure that their numerical simulations conserve energy and angular momentum over billions of simulated years. Machine learning and artificial intelligence are also being brought to bear on this problem. Neural networks can be trained to recognize patterns in orbital data that might indicate past perturbations. They can process vast amounts of observational data, looking for subtle correlations that human analysts might miss. As these techniques improve and more data becomes available, our ability to detect the echoes of past cosmic events will continue to enhance. The search for echoes of 3i Atlas is part of a broader effort to understand the dynamical history of our solar system. Scientists are trying to reconstruct the solar system's entire biography, from its formation 4.6 billion years ago to the present day. This includes the early period of planetary migration, the late heavy bombardment when the inner planets were pelted with asteroids and comets, the gradual evolution of orbits due to planetary interactions, and yes, the occasional perturbation from interstellar visitors. Each piece of evidence we find adds to this reconstruction. The cratered surfaces of the Moon and Mercury tell us about ancient impacts. The current orbits of the planets constrain models of planetary migration. The distribution of asteroids and Kuiper Belt objects provides clues about past dynamical events. And now, the passage of 3i Atlas adds a new chapter to this story. A reminder that the solar system's evolution has been influenced not just by internal processes, but also by external visitors from the wider galaxy. The philosophical implications of this search are profound. We're essentially trying to prove that a brief cosmic encounter, lasting just a few months, has left a permanent mark on our solar system that will persist for billions of years. It's a testament to the deep interconnectedness of the universe, where even fleeting interactions can have lasting consequences. Every gravitational interaction, no matter how small, leaves its signature in the cosmic dance, contributing to the complex choreography we observe today. The search also highlights the importance of long-term thinking in astronomy. Many of the effects we're looking for will only become clearly detectable over decades or centuries of observation. This requires a continuity of effort that spans human generations, with astronomers today laying the groundwork for discoveries that might not be made until long after they're gone. It's a humbling reminder that science is a collective enterprise that transcends individual lifetimes. International cooperation is essential to this search. Observations from telescopes around the world and in space must be combined to achieve the necessary precision. Data must be shared freely among scientists regardless of nationality. Standards must be agreed upon for how observations are made and reported. The search for echoes of 3i Atlas, like astronomy in general, brings humanity together in a common quest to understand our cosmic environment. As our technology improves, we'll be able to detect ever fainter echoes of past events. Future space missions might place laser retroreflectors on other planets, allowing us to measure their positions as precisely as we now measure the moons. Gravitational wave detectors might become sensitive enough to detect the waves generated by planetary motion. Quantum sensors might achieve precisions we can barely imagine today. Each technological advance will allow us to hear fainter whispers from the cosmic past. The discovery of 3i Atlas and other interstellar objects has also inspired new observational strategies. Astronomers are now actively searching for more interstellar visitors, knowing that each one provides a new opportunity to study both the object itself and its gravitational influence on our solar system. Survey telescopes are being optimized to detect fast-moving objects. Alert networks are being established to quickly notify observers worldwide when a new interstellar object is discovered. The goal is to detect these visitors as early as possible, maximizing our opportunity to study them. Some scientists have proposed even more ambitious projects. Imagine a network of spacecraft stationed throughout the solar system, continuously monitoring the positions of planets and asteroids with unprecedented precision. Such a network could detect tiny orbital perturbations in real time, immediately alerting us to the gravitational influence of passing objects. It could also serve as an early warning system for potentially hazardous asteroids, combining scientific research with planetary defense. The search for echoes of 3i Atlas also connects to fundamental physics. General relativity predicts tiny corrections to Newtonian gravity that affect planetary orbits. By precisely measuring these orbits, we can test Einstein's theory in the weak field regime. Any deviation from the predictions of general relativity would be a major discovery, potentially pointing toward new physics. The perturbations from 3i Atlas, while complicating this analysis, also provide additional data points for testing gravitational theories. As we search for these echoes, we're also building a library of orbital evolution that will be valuable for future generations. Every observation we make, every orbital determination we calculate, adds to this library. Future astronomers will be able to look back at our data, combined with their own observations, to detect changes that we cannot yet see. We're creating a legacy of precision measurement that will enable discoveries we cannot yet imagine. The echoes we're searching for are not just in the motions of planets and asteroids, they're also in the distribution of dust and gas in the solar system. As 3I Atlas sublimated, it released dust and gas that became part of the interplanetary medium. Some of this material might have been captured by planets or moons. Some might have been blown out of the solar system by the solar wind. But some remains, orbiting the Sun, a physical remnant of the comet's passage. Future missions might be able to detect and analyze this material, finding isotopic signatures that confirm its interstellar origin. The search for echoes also extends to Earth itself. If 3I Atlas shed dust particles that reached Earth's atmosphere, some of them might have survived to the ground as micrometeorites. These particles would have unusual isotopic ratios, marking them as interstellar in origin. Scientists are searching for such particles in Antarctic ice, where micrometeorites accumulate and are preserved. Finding even a single grain that can be definitively linked to 3I Atlas would be a remarkable discovery, providing direct physical evidence of the comet's passage. Time itself becomes a tool in this search. The longer we observe, the more precisely we can determine orbits and detect small changes. Every year of additional data improves our ability to hear the echoes of past events. This is why astronomical archives are so valuable. Observations made decades ago, when combined with modern data, can reveal changes that neither data set alone could show. We're building a temporal telescope, using time as a lens to bring past events into focus. The search for echoes of 3I Atlas is teaching us patience. In our fast-paced world, we're accustomed to quick answers and immediate results. But the cosmos operates on its own timescale, indifferent to human impatience. The echoes we're searching for unfold over centuries and millennia. Detecting them requires a kind of scientific meditation, a careful attention to tiny details that might easily be overlooked. It's a reminder that some of nature's secrets reveal themselves only to those willing to watch and wait. As we continue this search, we're also preparing for future interstellar visitors. Each one will provide another opportunity to study these cosmic wanderers and their gravitational influences. By comparing the effects of different interstellar objects, we can learn about the range of masses, compositions, and trajectories of these visitors. Over time, we'll build up a statistical understanding of the population of interstellar objects in our galaxy, learning about the processes that eject them from their parent systems and send them wandering through space. The echoes of 3I Atlas might also be found in unexpected places. Perhaps the comet's passage triggered a small landslide on an asteroid, changing its surface in a way we might someday detect. Perhaps it perturbed a dormant comet in the Oort cloud, setting it on a path that will bring it into the inner solar system millions of years from now. Perhaps it influenced the orbit of a piece of space debris from one of our own spacecraft, creating an artificial echo of its passage. The possibilities are limited only by our imagination and our ability to detect subtle changes. As night deepens around you and you drift deeper into contemplation, consider that you are surrounded by echoes of cosmic events. The light from stars carries echoes of nuclear fusion that happened years, centuries, or millennia ago. The warmth you feel from your surroundings carries echoes of sunlight absorbed by Earth. The very atoms in your body carry echoes of stellar explosions that occurred billions of years ago. We live in a universe of echoes, where every event sends ripples through space and time that never completely fade away. The search for echoes of 3I Atlas is just one example of how we're learning to hear these cosmic reverberations. As our instruments become more sensitive and our techniques more sophisticated, we'll be able to detect fainter and fainter echoes reaching further back in time, uncovering events that shaped our solar system in ways we're only beginning to understand. Each echo we detect adds another thread to the tapestry of cosmic history, helping us understand not just where we are, but how we got here. The cosmic butterfly effect is perhaps one of the most beautiful and unsettling concepts in modern physics. It suggests that in certain systems, tiny changes can cascade through time, amplifying into large-scale differences that reshape entire worlds. When we consider 3I Atlas through this lens, we're not just thinking about a comet that passed through our solar system. We're contemplating how a cosmic pebble dropped into our gravitational pond might send ripples extending millions of years into the future, subtly but fundamentally altering the trajectory of planetary evolution. Edward Lorenz, the meteorologist who discovered this phenomenon, stumbled upon it almost by accident while running weather simulations on an early computer. He found that rounding a number from 0.506127 to 0.5006, a difference of about 1 part in 10,000, completely changed his weather prediction after just a few simulated days. This sensitive dependence on initial conditions has since been found in many natural systems, from the dripping of faucets to the fluctuations of animal populations to the orbits of planets around stars. In our solar system, this butterfly effect operates on timescales that dwarf human experience. A change in Earth's velocity of just 1 millimeter per second, slower than a snail's pace, would cause Earth to be in a completely different position in its orbit after just a few million years. Not a different orbit, mind you, but a different position in the same orbit, arriving at each point slightly earlier or later than it would have otherwise. This might seem like a trivial difference. But when we consider that Earth's position relative to other planets determines their mutual gravitational interactions, we begin to see how small changes can cascade into larger effects. Imagine Earth as a cosmic timekeeper, its orbital period setting a rhythm that influences everything else in the solar system. If 3I Atlas changed this rhythm even slightly, it would affect when Earth and Jupiter are closest together, when Earth and Mars align, when Earth passes through the debris streams that create meteor showers. Each of these events would happen at slightly different times, and these timing differences would accumulate and interact in complex ways. Over millions of years, the entire choreography of the solar system would subtly shift, like a symphony where one instrument is playing at a slightly different tempo. The mathematics of chaos tells us that there are certain regions of possibility, what scientists call phase space, where orbits are stable and predictable, and other regions where they become chaotic and unpredictable. Our solar system currently resides in a stable region, which is why we can predict eclipses centuries in advance and send spacecraft to distant planets with precise timing. But we're not infinitely far from the chaotic regions. Given enough perturbations over enough time, planetary orbits could theoretically shift from stable to chaotic behavior. This doesn't mean the planets would suddenly fly off in random directions. Chaos in orbital mechanics is more subtle than that. It means that small differences in initial conditions lead to dramatically different outcomes over time. Two solar systems that start out nearly identical might evolve in completely different ways. In one, Earth might maintain its nearly circular orbit for billions of years. In another, Earth's orbit might become more elliptical, leading to extreme seasons that make the planet uninhabitable. The difference between these outcomes might hinge on something as small as the passage of an interstellar comet. The butterfly effect from 3I Atlas wouldn't operate in isolation. It would interact with all the other chaotic processes in the solar system. The asteroid belt, for instance, is a chaotic system where asteroids' orbits can change dramatically due to repeated planetary perturbations. If 3I Atlas shifted even one asteroid onto a slightly different orbit, it could trigger a cascade of collisions and gravitational interactions that reshape the entire belt over millions of years. Some asteroids might be thrown into the inner solar system, potentially impacting planets. Others might be ejected entirely, becoming interstellar objects themselves. Jupiter plays a special role in this cosmic butterfly effect. As the most massive planet, Jupiter's gravitational influence extends throughout the solar system. It acts as both a shepherd and a scatterer, maintaining the stability of some orbits while disrupting others. If 3 Atlas caused even a tiny change in Jupiter's orbit, this change would be amplified through Jupiter's interactions with other bodies. It's like adjusting the position of a lighthouse. Even a small shift changes where the beam of light falls across a vast area. The concept becomes even more intriguing when we consider resonances. Many bodies in the solar system are locked in orbital resonances, where their periods form simple ratios. These resonances can be stable, maintaining orbital relationships for billions of years, or unstable, leading to chaotic evolution. A small perturbation from 3I Atlas might push a body closer to or farther from a resonance, fundamentally changing its long-term orbital evolution. It's like gently adjusting the tuning of a guitar string. A small change in tension can shift the harmonic relationships throughout the instrument. Climate scientists have found that Earth's climate system exhibits butterfly effects on multiple timescales. The famous Milankovitch cycles, driven by changes in Earth's orbit and rotation, can trigger ice ages or warm periods. If 3I Atlas altered Earth's orbital parameters even slightly, it might shift the phase or amplitude of these cycles. An ice age that would have begun in 50,000 years might instead begin in 45,000 years, or might be more or less severe. While this wouldn't affect us or even our distant descendants, it could profoundly influence the evolution of life on Earth over geological timescales. The butterfly effect also operates through the solar system's interaction with the galaxy. As our solar system orbits the galactic center, it oscillates up and down through the galactic disk, sometimes passing through regions of higher stellar density or through molecular clouds. If 3I Atlas changed the solar system's velocity even slightly, it might affect when these passages occur. A passage through a dense molecular cloud that would have happened in 30 million years might instead happen in 29 million years. This could affect the rate of comet impacts on Earth, the amount of interstellar dust entering the solar system, even the rate of cosmic rays reaching Earth's surface. Consider the formation of Earth's moon, believed to have resulted from a Mars-sized object colliding with the early Earth. This impact had to happen at just the right angle and velocity to create our unusually large moon, rather than destroying Earth or creating a ring system. If the proto-Earth's orbit had been even slightly different, this impact might not have occurred, or might have had a different outcome. Earth might have no moon, or multiple small moons, or rings like Saturn. The butterfly effect suggests that tiny differences in the early solar system, perhaps caused by interstellar visitors like 3I Atlas, could have led to dramatically different planetary configurations. The fragmentation of 3I Atlas adds layers of complexity to the butterfly effect. Each fragment represents a separate perturbation, a separate butterfly flapping its wings. These multiple perturbations might interfere constructively in some cases, amplifying each other's effects, or destructively in others, cancelling out. The pattern of fragmentation, how many pieces, their sizes, their velocities, becomes crucial in determining the long-term consequences. It's as if instead of a single butterfly, we had a whole swarm, each contributing its own small effect to the weather patterns. This cosmic butterfly effect extends to the biological realm as well. The history of life on Earth has been shaped by astronomical events, asteroid impacts, changes in solar radiation, variations in Earth's orbit and climate. If 3I Atlas shifted Earth's orbit even slightly, it might affect the timing or severity of future extinction events or evolutionary pressures. A slightly different orbital configuration might mean more or less radiation reaching Earth's surface, different patterns of seasons, different ocean currents. Over millions of years, these differences could lead to entirely different evolutionary outcomes. Imagine an alternate Earth where 3I Atlas passed a bit closer, exerting a stronger gravitational pull. Earth's orbit becomes slightly more elliptical. Summers in one hemisphere become hotter, winters colder. This changes weather patterns, ocean currents, the distribution of ice. Different regions become habitable or uninhabitable. Migration patterns of animals change, evolutionary pressures shift. Given millions of years, the biosphere evolves differently. Perhaps mammals never become dominant. Perhaps intelligence evolves in a different lineage. The entire history of life on Earth, including our own existence, might hinge on such cosmic contingencies. The butterfly effect from 3-Eye Atlas might also influence technological development. Many of our technologies depend on precise knowledge of planetary positions, GPS satellites, deep space communication, interplanetary navigation. If planetary orbits are slightly different than they would have been, we might need to adjust these technologies. More fundamentally, if the butterfly effect from past interstellar visitors influenced Earth's geological or biological history, it might have affected the resources available to us, where oil deposits formed, where metal ores concentrated, even where fertile soils developed. Philosophically, the cosmic butterfly effect challenges our notions of determinism and free will. If the current state of the solar system depends sensitively on random encounters with interstellar objects, then our existence itself contains an element of cosmic chance. We're here not just because of the laws of physics, but because of the specific history of random events that shaped our solar system. This adds a layer of contingency to our existence that's both humbling and awe-inspiring. The butterfly effect also has implications for the search for extraterrestrial life. If planetary systems are chaotic, sensitive to small perturbations from interstellar visitors, then even systems that start out very similar might evolve in dramatically different ways. Two stars with identical protoplanetary disks might end up with completely different planetary configurations due to different histories of interstellar encounters. This might help explain the remarkable diversity of exoplanetary systems we've discovered, where hot Jupiters orbit close to their stars and super-Earths exist in configurations unlike anything in our solar system. As we project forward in time, the butterfly effect from 3-Eye Atlas becomes increasingly uncertain. We can calculate with reasonable precision where the planets will be in 1,000 years, somewhat less precisely in 10,000 years, and only roughly in 1,000,000 years. Beyond that, the uncertainty grows exponentially. The butterfly effect from 3-Eye Atlas, combined with all the other chaotic influences in the solar system, means that the far future configuration of our solar system is fundamentally unpredictable. This unpredictability isn't a failure of science, but a fundamental property of chaotic systems. Even with perfect knowledge of current conditions and infinite computational power, we couldn't predict the exact state of the solar system billions of years from now. The butterfly effect ensures that tiny influences we can't possibly account for, the gravitational pull of a distant asteroid, the pressure of sunlight on a dust grain, the passage of an interstellar visitor, will eventually grow into large-scale changes. Yet within this chaos there are islands of stability. The solar system has mechanisms that resist perturbations, negative feedback loops that maintain orbital stability. The planet's mutual gravitational interactions tend to average out random perturbations over time. Orbital resonances can lock bodies into stable configurations that persist despite small disturbances. It's this balance between chaos and stability that has allowed Earth to maintain a habitable environment for billions of years despite countless perturbations. The study of the cosmic butterfly effect has practical applications. By understanding how small perturbations can grow over time, we can better assess the long-term stability of satellite orbits, the risk of asteroid impacts, and the evolution of space debris. We can design spacecraft trajectories that take advantage of chaotic dynamics, using small course corrections to achieve large changes in destination. We can better understand the limits of predictability in various systems, knowing when long-term forecasts are reliable and when they're not. As our ability to detect and track interstellar objects improves, we'll be able to study the cosmic butterfly effect in real time. Each new visitor will provide a natural experiment in how small perturbations affect the solar system. By carefully tracking the orbits of planets and asteroids before and after these encounters, we can measure the butterfly effect directly. Over time, we'll build up a statistical understanding of how these random perturbations influence solar system evolution. The cosmic butterfly effect also connects to quantum mechanics in intriguing ways. At the quantum level, the universe is fundamentally probabilistic, with particles existing in superpositions of states until observed. Some physicists speculate that quantum effects might occasionally amplify to macroscopic scales through chaotic dynamics. A single quantum event, the decay of a radioactive atom, the emission of a photon, might through a long chain of cause and effect influence the trajectory of an asteroid or comet. If true, this would mean the solar system's evolution contains an element of quantum randomness, making it fundamentally unpredictable even in principle. As you contemplate these ideas in the quiet darkness, consider that your own thoughts might be exhibiting butterfly effects. A single neuron firing in your brain triggers others to fire, creating cascades of activity that result in thoughts, decisions, actions. These actions influence others, who influence still others, creating ripples that spread through society. A kind word spoken today might, through a long chain of influences, change someone's life years from now. We're all butterflies, creating effects that ripple outward in ways we cannot predict or control. The cosmic butterfly effect reminds us that we live in a universe where everything is connected, where small causes can have large effects, where the future is not predetermined but constantly being created through the interaction of countless influences. The passage of 3 Atlas through our solar system was one such influence, a cosmic butterfly whose wings are still creating ripples that will continue to propagate for millions of years. We cannot know exactly how these ripples will evolve, what changes they will ultimately cause, but we can appreciate the beauty and complexity of a universe where such effects are possible. In this cosmic context, our lives take on new meaning. We are not just passive observers of a predetermined cosmic drama, but active participants in an unfolding story whose ending is not yet written. Every action we take, every decision we make, sends ripples through the fabric of reality that will continue long after we're gone. We're all part of the cosmic butterfly effect, our lives intertwined with the motion of planets, the passage of comets, the evolution of the universe itself. The beauty of unanswered questions surrounds us like a gentle mist on a quiet morning, soft and encompassing, inviting us to wonder rather than to know with certainty. As we near the end of our contemplation of 3I Atlas and its possible influence on planetary orbits, we find ourselves not with definitive answers, but with something perhaps more valuable, a deep appreciation for the magnificent mysteries that pervade our universe. These unanswered questions are not failures of science, but invitations to continued exploration, reminders that the cosmos is far richer and more complex than our current understanding can fully grasp. Consider for a moment the fundamental question we've been exploring. Did 3I Atlas actually shift the orbits of our planets? Despite all our sophisticated instruments, our powerful computers, our elegant mathematics, we cannot answer this question with absolute certainty. The expected perturbations are so small, the uncertainties in our measurements so relatively large, that the truth remains tantalizingly out of reach. And perhaps this is as it should be. Perhaps the universe maintains some of its mysteries not to frustrate us, but to keep us curious, to ensure that there will always be something new to discover, always another reason to look up at the stars in wonder. The uncertainty surrounding 3I Atlas's influence is itself a profound lesson about the nature of knowledge. We live in an age that often demands immediate answers, definitive conclusions, absolute certainty. But the cosmos operates on its own terms, revealing its secrets slowly, partially, sometimes ambiguously. The story of 3I Atlas teaches us patience and humility. It reminds us that some questions require not just days or years, but decades or centuries to answer. Some questions might never be fully answered, and yet they remain worth asking because the search itself enriches our understanding. What we do know about 3i Atlas raises far more questions than it answers. Where exactly did this cosmic wanderer come from? Around which distant star did it form, and how long ago? What caused it to be ejected from its home system? How many other star systems did it pass through on its long journey to ours? Each of these questions opens up entire fields of inquiry, entire careers worth of research. The comet is gone, continuing its journey through interstellar space. But the questions it raised will occupy scientists for generations to come. The fragmentation of 3i Atlas presents its own beautiful mysteries. Why did it break apart when it did? Was it simply thermal stress from the sun's heat? Or was there something unusual about its internal structure? Did it consist of loosely bound rubble, held together by weak forces, or was it a more solid body that catastrophically failed? The way it fragmented might tell us something profound about how comets form in different stellar environments, about the processes that create these cosmic wanderers. But with the comet now gone and only limited observations of its breakup, these questions remain open, inviting speculation and further study. There's something deeply satisfying about questions that resist easy answers. They remind us that the universe is not a puzzle to be solved, but a mystery to be experienced. Each answer we find reveals new questions, like opening a door only to find a hallway with many more doors. This infinite regress of discovery ensures that science will never be finished, that there will always be frontiers to explore, always be surprises waiting in the cosmic darkness. The question of whether 3i Atlas shifted planetary orbits connects to larger questions about the nature of causation in complex systems. In a system as intricate as our solar system, with multiple bodies all influencing each other, how do we assign causation to any particular event? If Earth's orbit is slightly different in a million years, was it because of 3i Atlas, or because of the countless asteroids that pass by, or because of the gradual evolution of planetary interactions? Perhaps the question itself is wrong. Perhaps we need to think not in terms of single causes, but in terms of webs of influence, networks of interaction where every element contributes to the whole. This interconnectedness raises philosophical questions about the nature of identity and persistence. If 3i Atlas did shift Earth's orbit, even minutely, is Earth still the same planet it would have been otherwise? The atoms are the same, the mass is the same, but the trajectory through space is different. Over millions of years, this different trajectory means Earth will be in different places at different times, experiencing different gravitational influences, different amounts of sunlight, different cosmic ray fluxes. In what sense is it the same Earth, and in what sense is it different? These questions might seem abstract, but they touch on fundamental issues in physics and philosophy. They're related to questions about determinism and free will, about the nature of time and causation, about what it means for something to exist and persist through change. The passage of 3i Atlas through our solar system provides a concrete example to ground these abstract discussions, a real event whose consequences we can contemplate even if we can't fully calculate them. The beauty of these unanswered questions extends to the nature of interstellar objects themselves. We've now detected 3 confirmed interstellar visitors, each one different from the others. Oumuamua was elongated and showed no cometary activity. 2i Borisov was clearly a comet but with unusual properties. 3 Atlas was a fragmenting comet with its own unique characteristics. Are these objects representative of the broader population of interstellar wanderers, or are they outliers? How many different types of interstellar objects are there? What can they tell us about planet formation in other star systems? Each interstellar visitor raises the tantalizing possibility that we're sampling material from specific, identifiable star systems. If we could trace 3i Atlas back to its origin, we would learn not just about the comet, but about conditions around another star, possibly one very different from our Sun. We would be doing astronomy not by observing distant stars with telescopes, but by examining actual pieces of those systems that have travelled to us. It's a form of cosmic archaeology that we're only just beginning to explore. The questions raised by 3i Atlas also touch on the possibility of life elsewhere in the universe. If comets can travel between star systems, could they carry organic molecules or even microorganisms from one system to another? This idea, called panspermia, suggests that life might spread through the galaxy like seeds on the wind. While we found no evidence of life on 3i Atlas, the possibility remains for future interstellar visitors. Each one might carry chemical or even biological signatures from its home system, messages written in molecules rather than words. The timing of 3i Atlas's visit raises its own questions. Why did it arrive when it did? Pure chance, of course, but what are the odds? If interstellar objects are common, why have we detected so few? Is it just that our detection capabilities have improved? Or was there something special about recent years that brought multiple interstellar visitors our way? Perhaps we're passing through a region of space with a higher density of such objects. Perhaps there was some event in our galactic neighbourhood millions of years ago that ejected many comets from their home systems, and we're just now encountering the wave of refugees. The question of gravitational influence extends beyond just our solar system. If 3i Atlas could potentially shift planetary orbits here, then our own comets and asteroids that get ejected must be causing similar perturbations in other star systems. We're not just recipients of cosmic influence, but also sources of it. Somewhere in the galaxy, billions of years from now, a comet that originated in our solar system might pass through another planetary system, potentially shifting orbits there. We're all part of a vast network of gravitational exchange, giving and receiving influences across the light years. This raises profound questions about cosmic responsibility and connection. In a very real sense, what happens in our solar system doesn't stay in our solar system. The asteroids we accidentally perturb onto escape trajectories become interstellar messengers. The spacecraft we've sent beyond the solar system, like the Voyagers and Pioneers, will eventually pass through other star systems. We're already participants in the cosmic community, whether we realize it or not. The unanswered questions about 3i Atlas also highlight the limitations of our current technology and understanding. We can detect these objects only when they come relatively close to the Sun, and only if they're large enough and bright enough. How many smaller interstellar objects pass through undetected? How many zip through the outer solar system without ever coming close enough for us to see? We might be seeing only the tip of the iceberg, the few objects that happen to pass close enough and be large enough for our telescopes to spot. Future technology might allow us to answer some of these questions. Imagine a network of telescopes throughout the solar system, constantly scanning for interstellar visitors. Imagine spacecraft ready to intercept these objects, to study them up close, perhaps even to return samples to Earth. Imagine computer simulations powerful enough to trace the gravitational influences of thousands of objects over billions of years. Each advance in technology will allow us to ask new questions, to probe deeper into the mysteries that 3i Atlas has revealed. But even as technology advances, new questions will arise. This is the beauty of science. It's not a process of replacing mystery with knowledge, but of replacing simple mysteries with more sophisticated ones. The questions we ask today would have been incomprehensible to astronomers a century ago, and the questions astronomers will ask a century from now might be incomprehensible to us. Each generation stands on the shoulders of the previous one, seeing a bit farther, asking slightly deeper questions. The mystery of 3i Atlas's potential orbital influence also connects to questions about the stability and uniqueness of our solar system. We've discovered thousands of exoplanetary systems, many with configurations very different from ours. Some have hot Jupiters orbiting close to their stars, others have super-Earths in compact orbits. Still others have planets on highly elliptical or inclined orbits. Is our solar system's relatively orderly arrangement common or rare? Did interstellar visitors play a role in creating this arrangement, Or would it have emerged anyway? These questions matter for understanding our place in the universe. If solar systems like ours are rare, if they require just the right history of formation and perturbation, then Earth-like planets might also be rare. But if many different histories can lead to habitable worlds, if life is robust against orbital variations, then the universe might be teeming with life. The passage of 3i Atlas reminds us that these questions are not just about abstract physics, but about our cosmic context, about whether we're alone or part of a vast community of living worlds. The unanswered questions extend to the nature of scientific knowledge itself. How do we know what we know? How certain can we be about events we didn't directly observe? The potential orbital changes from 3i Atlas, if they occurred, happened over such long timescales that no human could observe them directly. We must infer them from models, from simulations, from indirect evidence. This raises epistemological questions about the nature of scientific truth, about how we construct knowledge about events too slow or too fast, too large or too small for direct human observation. As you rest there in the peaceful darkness, surrounded by these beautiful uncertainties, perhaps you can feel a different kind of knowledge, one that doesn't require definitive answers. It's the knowledge that comes from wonder, from appreciation, from recognizing our place in something vast and mysterious. The questions raised by 3i Atlas are gifts, invitations to continued curiosity, reminders that the universe is far stranger and more wonderful than we might have imagined. The beauty of unanswered questions is that they keep us humble. Despite all our achievements, despite our ability to detect objects from other star systems and calculate their trajectories, we remain beginners in our understanding of the cosmos. Every answered question reveals 10 new questions. Every certainty is surrounded by uncertainties. This is not a weakness of science, but its greatest strength. The recognition that there's always more to learn, always deeper levels of understanding to achieve. Consider how the question of 3i Atlas's influence will be viewed by future generations. Perhaps in a century, with more precise observations and better models, scientists will definitively answer whether the comet shifted planetary orbits. Or perhaps they'll discover that the question was poorly framed, that we were thinking about the problem in the wrong way. Perhaps they'll have detected hundreds more interstellar visitors, making 3 Atlas just one data point in a vast statistical understanding of such objects. Or perhaps 3 Atlas will remain special, the comet that first made us realize how interstellar visitors might influence planetary evolution. The questions we cannot answer today become the research programs of tomorrow. Young scientists, perhaps not yet born, will take up these questions, approaching them with new tools and new perspectives. They'll build on our observations, our models, our tentative conclusions. They'll correct our errors and extend our insights. This is how science progresses, not through definitive answers, but through successive approximations, each generation getting a bit closer to understanding, even as that understanding reveals new depths of mystery. The beauty of unanswered questions also lies in their democracy. While experts might have more informed speculations, no one knows for certain whether 3 Atlas shifted planetary orbits. In the face of true mystery, we are all equal. We can all wonder, all imagine, all contribute our perspectives. The questions belong to everyone, inviting participation from anyone curious enough to contemplate them. As we approach the end of our journey with 3i Atlas, we find that the questions have become more important than the answers. The comet has served its purpose not by providing certainty, but by opening our minds to possibilities we hadn't considered. It has shown us that our solar system is not isolated, but connected to the wider galaxy through threads of gravity and exchanges of matter. It has reminded us that the cosmos is dynamic, that change is constant even on astronomical scales, that nothing is permanent except change itself. The unanswered questions about 3 Atlas will outlive us all. Long after we're gone, astronomers will still be studying interstellar visitors, still trying to understand their influences on planetary systems, still marveling at the complexity and beauty of gravitational interactions. The questions we've explored tonight will evolve, becoming more sophisticated, more precise, but they'll retain their essential mystery. And that's as it should be. A universe without mystery would be a universe without wonder, and a universe without wonder would be a universe not worth contemplating. In the end, perhaps the most beautiful aspect of these unanswered questions is that they connect us to the infinite. Every question about Three-Eye Atlas opens onto larger questions about the nature of the universe, the origins of solar systems, the possibilities for life, the meaning of existence itself. We started by asking whether a comet might have shifted planetary orbits, and we've ended up contemplating our place in the cosmos. This is the power of sincere questioning. It leads us always deeper, always toward more profound mysteries. As sleep approaches and your consciousness begins to drift like Three-Eye Atlas itself into the vast darkness, carry with you not the burden of unanswered questions, but their beauty. Let them be like stars in your mental sky, points of light that guide wonder rather than demanding resolution. The universe has shared one of its mysteries with us through the passage of this interstellar visitor. We may never fully understand its influence, but in the attempt to understand, we've discovered something profound about the nature of our cosmic home. The questions remain, floating in the space between knowledge and mystery, between what we know and what we might someday discover. They are invitations to future wonder, promises that the universe will never run out of surprises, guarantees that there will always be reasons to look up at the night sky with awe. And in this space of beautiful uncertainty, in this realm of unanswered questions, we find not frustration but peace, not anxiety but wonder, not endings but infinite beginnings. Three-Eye Atlas has completed its passage through our solar system and returned to the interstellar darkness. But the questions it raised remain with us, gifts from a cosmic visitor, reminders of how much we have yet to learn. And perhaps that's the most beautiful answer of all, that the universe is generous with its mysteries, always offering more questions than we can answer, always inviting us deeper into wonder. In this generosity, in this infinite invitation to curiosity, we find our purpose as conscious beings in a vast and mysterious cosmos. We are the universe's way of asking questions about itself, and every unanswered question is a promise that our purpose will never be exhausted. As long as there are mysteries like Three-Eye Atlas, as long as there are questions about gravitational influences and orbital evolution, and the connections between star systems, we will have reasons to wonder, reasons to explore, reasons to dream. The beauty of unanswered questions is that they make us fully human, fully alive to the possibilities that surround us in every direction, extending outward to the stars and inward to the depths of contemplation. And so we end where we began, not with certainty but with wonder, not with answers but with appreciation for the questions themselves. Three-Eye Atlas has given us a gift more valuable than any definitive conclusion. It has reminded us that we live in a universe where a piece of another star system can visit ours, where tiny influences can have vast consequences, where mystery and beauty are woven into the very fabric of existence. In accepting this gift, in embracing these unanswered questions, we become part of the cosmic conversation, participants in the eternal dialogue between consciousness and cosmos, between the known and the unknown, between what is and what might be. Sleep now, cradled by these beautiful uncertainties, floating in the space between questions and answers, drifting like Three-Eye Atlas itself through the vast darkness that is not empty but full of possibility. The questions will be there when you wake, patient and eternal, waiting to carry you once again into wonder. And perhaps, in your dreams, you'll find not answers but something better, a deep peace with the mystery itself, a recognition that in a universe of unanswered questions, we are never finished discovering, never completed with our journey, always at the beginning of infinite exploration.